I don't think we went back. I don't think we went back and talked how that theory applied to the J-pole antenna theory.
Okay, a J-pole is, this is a J-pole. Yeah. Okay, so this is a J-pole. A J-pole is a half wavelength antenna. All right. So if it's a half wavelength antenna, that means that the current along it at the end, at the very top, has to be what?
Infinity.
No,
Well,
what's the
wait,
current? The current at the end of a piece of wire has to be
0.
zero. So that means that a half wave distribution, I can draw half a wave that looks like that. Okay. Now, at the bottom of the J pole, we have another piece of the antenna, right? If you've seen how a J pole looks, it kind of looks like this. And you connect the feed line right there. Right? Does that look familiar? That's why they call it a J pole, because the wire itself looks like a letter J. So here's my question to you. This piece of something hooked up to it right here, what is that?
The feed line.
That's the feed line, and it's usually twin lead, but it can be coax. Okay. What is this section right here? Does that look like something that would actually send out a signal?
Is that the ground?
No, that's actually a shorted piece of ladder line, a shorted piece of twin lead. And looking at this, if you have balanced um, balanced feed line feeding it, or you have matching but opposite currents, you have one over here and one over here, and then they're shorted together. So my question to you then is, Max, what do you think that portion of it does?
Well, let's
So I'm going to
see.
draw it like this. That's the part of the antenna that sends a signal off into space.
Okay.
And, and then you have another part of it, which you can think of as in parallel. These are really in parallel.
Okay.
This thing, number one, and this thing, number two. So here's your feed line,
Those are in parallel. Okay.
because this goes off into space, which you can think of as ground.
Okay, so space is ground. So,
And this is goes off into nothing, which we can also think of as ground. It's the end of the line for a signal.
well, it might act a little bit like a buffer, like a capacitor.
Yep,
Just
exactly right. This
okay.
is a matching network. And what would it be matching?
It would help be the transition from the antenna to the wire. So that would be the impedance matching. So
Perfect.
instead of having a transformer, you have a capacitor.
Yep,
Oh,
perfect.
okay.
So that bottom section of the J pole, the J section, is an impedance matching network.
Okay. And then I'm guessing the geometry relative to the antenna size, you can have different design parameters for that, like how far away that second wire needs to be, or
Well, the fact that it is a certain length, this is a well-defined number of, it's a well-defined fraction of a wavelength.
okay.
But it's also potentially based on, the separation between the wires and stuff like that. But that's why it works,
Mhm.
because you have feed line, which is typically 50 ohms. Now that's the roll-up J pole is fed by coax, but this section down here is usually 300 ohm twin lead. And this is just a piece of wire. The way you build a J pole is like this. You take a piece of two parallel wires, right?
Mhm.
And here's what's really interesting about this. They take the wire and they say, you want to notch it. you want to put a notch in it. And then you want to short down here and solder this to here and solder this to here. And then hook up your coax. So what does this element do?
Like a reflector.
That does nothing. But it's a lot easier to just leave it there than it is to cut it away. If you have molded cable, if this is a molded piece of ladder line, you just leave it there because it's a lot easier to just leave it. When I say, is everyone familiar with ladder line?
No,
No. Okay. I'm going to show you ladder line right now.
I was actually just getting ready to get on the iPad and look it up.
450 ohm ladder line. Here we go. That's ladder line.
Oh, okay, I got
Two
you.
parallel pieces of wire. Two parallel wires in a hard plastic shell.
Right.
So
Okay.
it's a lot easier to just leave it there.
Yeah,
That's
I've
what they
seen that. I just never knew the name.
Yeah,
That's the
it's what
same
they use
stuff
for the
on
old
TV.
yeah, over the air TV.
Yeah.
Right.
Well, actually, that was this. There's 300 ohm. Notice the difference between 300 and 450. The spacing is
Where-
different.
Uh-uh.
And then there's also 75 ohm parallel line. So you can have all these different impedances just by changing the spacing, which we talked about yesterday. See, isn't that cool? We're actually now able to apply all the stuff that we learned yesterday to real life.
And then I have one more follow-up question.
Yes, that's why I left the
So
board
when
up.
we have the J pole, sometimes there's that third pole there. Is that just like an extra capacitor?
Which
we-
one?
So someone happened to post an image in the chat of, inserting the J
Oh,
pole
no,
with
no,
the
no,
long
no, no, no,
antenna.
no, no. Yeah,
or is that
I know what
something
you're
else?
talking about. Oh,
Okay.
here we go. It looked like this. It was a copper. That was the copper cactus, right? And it looked like this.
Yeah.
Okay. Well, and this was shorted like right here. What purpose do you think that second thing does? This is a dual band J pole.
Yeah,
If it's a dual band J pole, what do you think that second thing is?
UHF.
That's a UHF radiator. Because they're going to be different lengths. So that's why it's there. Because it's for
Yeah.
another band.
Yeah, there's Signal Stuff company that makes them and sells them. They're
Mhm.
also in segments, so you can make it a portable rig.
Yeah, I have what I was saying now, this will make sense. I have a roll-up J pole that I take with me. And let's see, this is a roll-up J pole. Well, here we go. Can you share it? It costs almost nothing to build. See that? It's about 4 feet long. They call it a Slim Jim sometimes. Here's another one. Roll up antenna. That uses 300 ohm ladder line. I take one of these in my bag. I unroll it and I hang it from a like a curtain rod when I'm in a hotel. Works great. All right, everybody ready to start talking about other stuff? Today we're into modulation and signals and stuff like that. Everybody ready? Any other questions before we do? See, these questions are the best because they bring up all kinds of other applications and they make you realize how much you've really learned in 2 days. Right?
Yeah, I got one more.
Yes.
Uh, let me see what you think of this.
Robert in Sproul, Oregon.
Look at this picture.
What you got? That's being shown. Oh yeah, okay. That is, I believe is that harp, or is that a?
It's
r-
also referred to as the elephant cage, and there's
Wait,
only like they're about its military purpose, and there was 6 of them. This one happens to be in northern Japan.
I have no idea what that would be used for.
It's does 2 missions, I believe. It's SIGINT, signal intelligence, and then also DFing.
Is everyone familiar with something called HARP? HAARP?
Nope.
Mm,
High altitude atmospheric research project.
Oh yeah,
Yeah, its
it's in
job
the
was
middle
it's in the middle of nowhere. Its job
nowhere.
was basically to point up and create ionization in the sky and see what it did. So, yeah, that's HARP. A lot of people think it was trying to talk to aliens. I'm not so sure. Okay, here we go. Other questions before we go? Gonna have some fun today. Okay, here we go. Amateur radio signals. So we are on page number 57, if you're following along in the book. Okay, so notice we have lots of different modulation modes and signal bandwidth. We talked a little bit about what signals are and what bandwidth is the last 2 days. So for VHF and UHF voice repeaters, we typically use frequency modulation, which is FM, or PM, which is phase modulation. For VHF packet is a digital communications method over typically voice frequencies. So that's a digital communication. And since it's over voice frequencies, we typically use FM or PM. Amplitude modulation, one form of it is single sideband. We typically use single sideband when we're doing weak signal contacts on VHF and UHF, as well as the high frequency bands. Hey, everybody, what frequencies are high frequency bands? What are the ranges for high frequency? Come on, how many megahertz? The high frequency bands.
3 to
Is it
30.
3 to
300.
30. Yes. Okay. How about VHF?
30 to 300.
UHF?
Hmm.
What was UHF again?
300 to 3000.
Yep. Okay. All right. What sideband is normally used for 10-meter HF, VHF, and UHF? We're going to go over here and look at this chart.
At least I know what charts to look at.
Yes. So this chart that's up here, everything at 10 megahertz and up. So here's 10 megahertz, not 10 meters, but 10 megahertz. 10 megahertz and up uses upper sideband. Everything 10 megahertz and down uses lower sideband. So the 40-meter band would be lower sideband. 80 meters would be lower sideband. 10 meters would be upper sideband. All of VHF, UHF, if you're using sideband, is typically upper sideband. Okay, so bandwidths. So in order to do bandwidths, we're going to take a look at our web SDR again. So while that's coming up, I will continue on. The approximate bandwidth of a typical single sideband signal is 3 kilohertz. What does kilo mean, everybody?
1,000.
1,000. A VHF repeater signal which is FM, between 10 and 15 kilohertz. So what does that physically mean? That means that one signal takes up 15 kilohertz or 15,000 hertz of space. How does that compare to single sideband? Quite literally, it means you could stick 5 single sideband signals in the same bandwidth, because bandwidth is a resource, it's a physical thing. You could fit 5 single sideband signals inside a VHF FM signal. Disadvantages of FM: you can only receive one signal at a time. FM suffers from something called the capture effect, which means that only the strongest signal is the one that gets heard. The other ones disappear in the background. Now, why would we want to use FM? Typically, the fidelity is much higher, and because noise that's generated by static electricity, for instance, lightning, lightning and lightning strikes and sparks and things like that, the noise is typically an amplitude modulated thing, or AM. So FM is largely immune to static. We actually do this thing called fast scan TV. A fast scan TV signal takes up about 6 megahertz of bandwidth. So let's take a look at our frequency chart and take this with a grain of salt, realizing that our frequencies, we need, in order to do a full speed TV signal, we need 6 megahertz, not kilohertz, megahertz of bandwidth. So how wide is the entire 2-meter band? It goes from 144 to 148. You could not even fit a single TV signal in that band. So obviously we don't do that. However, 70 centimeters, which is the 420 to 450 band, this is 30 megahertz wide. And in fact, these 2 blocks here on the left, right here, those lower frequencies are actually used for television, believe it or not. Same on 33 centimeters, which is the 900 megahertz band. We use those. We use that for television. Up here, notice on the 23 centimeter band, we have, this is right here, 6 megahertz wide. This is 6 megahertz wide. This is 6 megahertz wide. Those are actually for amateur television. And in fact, believe it or not, in some places, they actually have amateur television repeaters, where you send a signal to an amateur television repeater, and it's full-time, full-screen, high-resolution video, and it's distributed to everybody who's listening, and then somebody else takes a turn. And instead of voice, you're actually sending video. That's known as amateur TV. But it requires a lot of bandwidth. And then you get to some very narrow bandwidth things. CW is continuous wave. It's our colloquial term for Morse code. A CW signal takes up not 150 kilohertz, but 150 hertz, which is very, very narrow. We have even narrower ones than that. We have something called PSK31, which takes up 31 hertz. That's a digital mode. That takes up literally 1/5 the width of a Morse code signal. So if I were to draw all of these, so here's FM, that's 15 kilohertz. And again, the reason we do this is because it's very high fidelity. So now we can do single sideband. Single sideband is 3000 hertz. We can also do amplitude modulation, which is AM, which everyone's heard of. That's 6000 hertz wide. And then we can do CW, which is 150 hertz wide. And then we can get down here and even do something narrower, which is PSK, which is 31 hertz wide. So how do we choose which one of these we use? Why would you pick one of these?
Depends on the information you want to send.
Depends on the information you want to send, depends on the conditions, depends on who's listening on the other end. If you know that, like for instance, PSK, this is essentially 31 hertz. This is keyboard typing speed. That's keyboard to keyboard. Morse code, 150 hertz. This is going to be as fast as I can send, like with a paddle. So, and I don't know if you can hear that or not.
We can hear it now.
There we go. So that's Morse code. Very narrow bandwidth. Single sideband. Why would you want to use single sideband even though it takes up a lot of space? Because you can speak. It can talk at 200 words a minute. You can carry a lot more information. Same with AM. Same with FM. You can send a lot more information a lot faster than you can using other modes that are narrow. So there's a fundamental rule that we have to learn from this. If there's one thing you take away from this, this is what I want you to learn. Okay, so what does that mean? Information requires bandwidth. What is the purpose of sending a signal over the radio waves? Over any communications method?
Communicate information.
Communicate information. The more information you send, the more bandwidth is required to do so. If you want to send something that's a very, very low information rate, you can get away with a very low bandwidth. It doesn't take up much space. Something that sends a lot of information requires a lot of bandwidth. So what if I'm doing Wi-Fi and I want 300 megabits per second? How much bandwidth am I going to take up? I'm going to take up a very, very wide swath of bandwidth. This is the fundamental thing I want you guys to get out of this, that information requires space to send it. It requires bandwidth. Bandwidth is a very valuable thing. Okay, let's see. The next thing to do is we're going to just cover a little bit about what things look like on the frequency spectrum. So this is an AM signal. This is my voice in amplitude modulation. If I were to look at this in time, here's a wave. What are some things I can do to this wave to change it? What are some fundamental properties of that picture?
Change the length.
I can change the length, which means I
Amplitude.
can shrink it, or I can expand it, which means I'm changing the wavelength, which means I'm also changing the
Frequency.
Okay, so I can alter the frequency. What else can I change?
Amplitude.
I can change the amplitude. What is amplitude, everyone?
Volume.
It's how big or how small. All right, so I can change the amplitude. What else can I change? What else is in there that I can alter?
The phase of the wave?
I can change the phase. Very good. So if I were to draw a wave that looked like this, how would I change the phase? I would physically shift this by a certain distance. Thinking back to that circle that we drew on the very first day in the very first few minutes, I'm basically changing the point on the circle where we're starting. So if I were sending a signal and I wanted to tell somebody that there was something happening that made them realize that they need to take notice of something, I could take this wave. Is there any information on this plain old sine wave? What do you think?
Besides the
Depends on
fact
the-
that it's on.
Well, let's just say that it sounds, I got the original sound on. It just sounds like this. And it goes forever. Other than it being there, is that conveying any information at all?
None.
None. One thing I can do to this is I can take this wave and I can do this with it. What am I doing with this wave now?
CW.
This is CW, continuous wave. This is called on-off keying. Oh, okay. I'm just turning it on and off. The presence or absence of this tells somebody that something is being done to it, right? If I take that and make it mean something, then I have Morse code. If I instead take a wave that looks like this, and I do this with it, but I keep the frequency basically constant, what is that telling somebody? If the amplitude was like 1, and up here the amplitude is 6, what is that telling someone?
Yes, sir. Talking?
Yeah, it's talking. You know, I'm using my voice or something to modulate the signal. Modulate means to change. So I'm basically using my voice to modulate the signal, and that means check the amplitude, because I increase the amplitude, and by my coding scheme, the amplitude changing means something. I can also do this. Get rid of that. Here we go. The amplitude stays the same. What am I changing here?
Frequency.
Okay, that's known as FM. I have told somebody that when you see a change in the frequency, that means I did something to change the frequency. If I do something and you know how to unwrap it, you can figure out what I did and what I meant to do. All right, I could also do this. I can be sending a signal and do this. What does that look like? Right there and right there. Those are jumps, right? The wave is exactly the same, but what have I done right here? I don't like the way that one came out.
Skip.
I skipped a piece of it. That's right. Well, if I skip a piece of it, here's another one. If I skipped a piece of it, it's not actually a skip of a piece. I actually shifted it, because this should have continued down, but instead I picked it up at another point. This is a phase shift. That's a change of phase right there. If I have phase modulation and I told somebody that when you see a shift of phase of a certain amount, that means I did something. It means if it's binary, it could be a value of a 1. If it's quadrature, it could be 2 bits, which means it could be, that means that if you see that particular phase, this translates to a value of 1, 1. This one translates to a value of 1, 0. If I now have 1, 1, 1, 0, and I told somebody, if you get a value of 1, 1, 1, 0, that's a letter A, what have I done?
Created a code.
I created a code. That's right. And now this is how I encoded the code so that it can get sent over the airwaves. This whole process is known as modulation. The process of taking it then taking it apart is known as
Demodulation.
demodulation. If you put those two words together, you get modulation and demodulation. And what do you get?
Modem.
Has anyone ever heard of a modem?
Uh, yeah,
That's where the word modem comes from. Modulator, demodulator.
started with a 9600.
I started with a 300.
Yeah.
Okay, so now what we're going to do is we're going to look at amplitude modulation, because this is one of the original forms of being able to send information. Amplitude modulation has a carrier right in the middle. This is the reference frequency, and it has two sidebands, an upper sideband and a lower sideband. These are mirror images of each other. Well, each of these is 3,000 hertz wide. So the total bandwidth that this takes up is 6,000 hertz. And it has a carrier. If you listen to an AM radio station, you will note you won't actually hear the carrier, but it's definitely there. If you listen to it in single sideband, you will hear a lot of power in the carrier. The carrier is just a marker. It carries information. It carries power necessary to generate sidebands. Well, what if on the receiver end I have my own carrier to put in and I don't need it? Then this is a waste of energy. The other thing is, what if my upper and lower sideband are truly mirror images of each other? Do I need to bother sending them both?
Nope.
So what we do at that point is we take one of the sidebands that we don't want and we filter it out before we transmit. Aha, there's that filter again. And we kill the carrier, and all we send is a sideband. So what we've done is we've been able to use our available power and not waste it in this or this, which makes it more efficient. And we also have shortened up our bandwidth. So we've saved space. And on the spectrum, can everybody see and hear? Make sure you can hear it. Boop, beep, beep. Okay, there we go. Now you should have audio. Everybody here okay?
Yeah.
Okay. Now we're going to take a look. Okay. Okay, so this is our received bandwidth. I want everybody to take a look. What is the approximate bandwidth? This goes from 14,205 to 14,208 kilohertz. What's our bandwidth?
3K.
3 kilohertz. Look at that. It really is. Here's another one. This bar on the vertical bar on the left, that's our carrier frequency. If this were AM, we would see a big bright line right there. But it's single sideband, so it's not sent. He's Russian. Yeah, somebody got that. He's Russian. Yep. So if you look at the band, you will see that there's a whole bunch of them. Here's another one. It's very popular, apparently. Here's another one. Italian. Another Italian. A lot of Italians on today. So now, okay, so we're going to go listen to another mode. This is a perfect example of what you can do with bandwidth. This is the same bandwidth, right? That's our same 3 kilohertz. Within this band, every one of those tones that you hear, every one of those annoying strings of tones, you can see them sort of dancing around on this picture. is a digital signal, all within one single sideband bandwidth. A lot lower data rate. They're digital communications, but we can fit about 40 of them in that same space.
So Scott, when you say it's a digital, does
Ones
that
and
mean
zeros.
somebody?
Ones and zeros.
Oh, okay. I'm
Computer
sorry.
to computer.
I got it. Never. Okay, never mind. Wrong. Bad question. My bad. Sorry.
No such thing. Here. Notice how narrow these are, Morse code. Again, much lower bandwidth, much lower data rate. But you can see that I can filter this way down and still get all the signal. So there are certain advantages to running narrow bands, narrow modes. It allows you to filter out adjacent signals very nicely.
Mhm.
I mean, that bandwidth is really tight. See this filter, 0.01 kilohertz? That's a 10 hertz wide filter, and we're still able to hear it. Ah, yes. Fun stuff. And you know what? Before I used to teach this class before there was such a thing as an SDR. This is such a great tool.
So now I have a question.
Yep.
Since our CW waves are also, I mean, to me, both the digital wave and the CW waves are just at one frequency. So I'm not quite understand why one's 5 times greater than the other.
Yeah. That's
Is it just tuning?
No, that's a tough one, isn't it? That's a tough one. Okay. So, has anybody gone through calculus?
I'll say yes.
Okay. Has anyone done Fourier transforms?
Unfortunately.
Yes. Okay.
No and no.
Fourier, Laplace. Okay. So, here is a question. If I were this is everybody, whether you've taken calculus or not, this is still for you. So I'm going to draw this. Okay, and I'm going to say this has a frequency of 1,000 hertz. If I look at this graph of the frequency, what am I going to see at 1,000 hertz? I'm going to see that there is only one frequency there, from 0 to infinity. Does everybody agree with that? If this is a pure sine wave of 1,000 hertz, I'm going to see that there is one frequency in existence at 1,000 hertz. Everyone agree with that?
Okay. Yes.
Okay.
Yeah.
What if I were to do this? And make a frequency of 2,000 hertz. Where would I see the green line? What frequency?
At 2000.
Yes, I'm decomposing it. Okay. Now, what if I did another one that was 3,000 hertz? I would see another one
At 3,000.
at 3,000 hertz. Right. Okay.
Okay.
Now, okay, we're all good so far, right? What now if I were to take all of these things and add them together, would that look like? It's a good question, isn't it? Well, here's where it gets really amazing. If I were to instead take that sine wave, which looks like this, start with that first sine wave at 1,000 hertz, and instead draw this. What is that called?
Well, it's a square wave.
It's a square wave. What's its frequency?
1,000 hertz.
It's 1,000 hertz. Yeah. Okay. Now, if I were to take a look at the frequency plot, I would find for the purple a pure sine wave, because it's a pure sine wave of 1,000 hertz. I think everyone agrees with that. What would happen with the green one? I'd have a line at 1,000 hertz, but then I'd also have a line at 3,000, and a line at 5,000, and a line at 7,000, all the way out to infinity. And they would get smaller and smaller the further out I went, in amplitude.
Like a harmonic.
They are harmonics. The more harmonics you add, the squarer the wave will get.
Oh,
This is called a Fourier analysis.
But why do they decrease?
Because the
Signal
amplitude
strength.
just gets smaller and smaller
Yeah.
in order to make that square wave. Square waves have the fundamental frequency plus all the odd harmonics above it. These are integer multiples are known as harmonics. Even harmonics will make it look different. Odd harmonics will make it look more like a square wave. And again, this is something called a Fourier analysis or Fourier decomposition. It's really amazing stuff when you start looking at it, because you have to look at it. You have to look at it from a frequency point of view rather than a time point of view, which is a little hard to get your head wrapped around. But because of that, we can do all kinds of frequency analysis based on things. When you start adding stuff together, the picture in time breaks down into a picture in frequency. So Fourier and Laplace were absolute geniuses because they could kind of see into this other world. And we have them to thank for the ability to generate pictures that look like, for instance, this. This right here is a real-time frequency plot. The fact that we can see this on a graph, they could never have pictured the fact that we could actually see these things in real time, because there was no processing power. This is done by mathematical calculation and an amazingly fast array of computers. And we just sort of take it for granted now. That make sense? Kinda?
yeah.
Okay. Okay, now where were we going with that? I think what it really comes down to is that it gives us the ability to visualize things in frequency as opposed to just time. Okay, so continuing along. Back to this. An electronic keyer. I have an electronic keyer. It looks like this. Make sure it's right side up. This is my electronic keyer. I'll share that. I'll stop sharing so you can see my picture. This is an electronic keyer. This is a Morse code paddle. This basically allows you to do this just by tapping the dits and the das back and forth, instead of actually having to pound out Morse code on a straight key. So that's an electronic keyer.
Wait, so are those technically different frequencies?
Oh, right.
Right next
so,
to each other?
Right. So here, okay. So here's where we were going with that. No, they are not. Right. So here's where we were going with that. The fact that I now have this square wave, right, which I'm turning on and off. Agree with that?
Yep.
This has let's say a pitch of 1,000 hertz when it's on. But I'm also turning it on and off. What does that look like?
CW.
Yeah, but what does it look like?
Mm,
Remember, what does it look like? This was for, oh, I'm trying to remember. I'm trying to remember the name. Was it Daniel who was asking this?
Me.
Max. Okay. What does that look like, Max?
I mean, it kind
We
of looks like a
just-
square wave.
It looks like a square wave. That's exactly right.
Yeah.
And what did we determine? What is the frequency of this square wave? Let's say that let's say you're doing this 10 times per second. Let's go even slower. Let's go 2 times per second.
So the fundamental frequency would be 2 hertz, and then
Yeah.
it has all the harmonics after that.
All the odd harmonics. So you'll have a 2, and then you'll have the third, which is 6 and 10 and 14 and 18 hertz. So even though you have a pitch of 1,000 hertz, right? It takes up bandwidth.
Okay.
That's where I was going with that.
So
And that's-
I'm guessing that all the lower frequencies are technically allocated to this frequency. So it's disjoint.
how do you mean?
So like, let's say the CW band is at 1,000 hertz. I don't know
There's-
if that's part of the rules or
No,
not.
no. Actually, the pitch has nothing to do with it.
Or the
The audio pitch has absolutely nothing to do with it.
So this is only the audio pitch.
Yeah, the audio pitch is just what you
Okay.
can hear.
Okay, so we need
The on-off speed is the overall thing that generates bandwidth. And here's the other thing. Because the pitch really doesn't exist. The pitch is actually just it really is just what you're listening to. So I'm going to unmute this, and I'm going to go here, and you're going to answer a question for me. If I move it, let's pick one that's not moving. Okay, let's go with this one. If I do that or move it, it sounds different, but did the guy making the signal in the first place change his frequency, yes or no?
He
No.
did not change the
He did
frequency.
not. He didn't do a thing. The only thing that's different is how I'm perceiving it. And how I'm perceiving it is actually generated locally in my receiver
Oh, you
Okay.
can hear it.
by changing the frequency and creating something called a beat frequency. So the way that works is I'm going to, actually, I don't want to share that. We're going to do a little experiment here because I love doing experiments. And I know this is going to be annoying, but here we go.
Sorry if this is a really long side.
Well, but it is, but it's actually really important. Okay, I'm going to open up. Okay. I'm going to run 2 things at once. Okay. Okay, here we go. You ready? Everybody prepare to be really annoyed? Okay. Here we go. Can everyone hear that?
Yes.
Yeah.
Yeah.
Can you hear this other one? Let me hit pause on that.
Oh no.
Can you hear them both?
Yeah. Yes.
Barely.
Okay,
Think-
let's try this.
I'll just say yes.
So it's an audible tone, 2 tones.
Can you hear that?
There we go.
Mm-hmm.
Mhm.
Oh, that.
Okay, is that really annoying?
Yes.
This is
Yeah.
called a beat. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so I'm going to stop this annoying sound. This is being done for a reason. That was a combination of 2 different tones. Those tones were 500 and 504 hertz. What is the difference of those tones
4
mathematically?
hertz.
4 hertz.
1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. These audio frequencies are like this, and like this. Slightly different.
A
And
fade.
4 times per second, they line up. That's known
Oh.
as a beat frequency.
Mm,
So
almost
by,
like a syncopation.
well, only because I chose them closely. So what if I took what if I took one and on the frequency chart that was right here, right? And that's 7.000010 megahertz. And then I took another one and I put it right here, 7.000060 megahertz. I could subtract those and I get a difference of 50 hertz. In my receiver, I will hear a 50 hertz tone. If I instead made this 660 hertz, I will hear a tone of 650 hertz. I didn't change the first one at all, did I? Just by creating a different one and hearing them both in the receiver, this is known as a beat frequency.
Why would you do that?
It's called a beat frequency oscillator, so that you could actually listen to something. A
Oh.
beat frequency oscillator allows you to listen to single sideband. It allows you to listen to Morse code. To allow you to generate a tone that you can then do something with. I said there's all kinds of cool stuff in here. I could go on
I have
forever.
a practical application question.
Hmm?
And as a ham operator, what
Yes.
can we do not to exceed bandwidth?
For the most part, you will know, you like, you're not allowed to transmit a single sideband signal more than, I think, like 4 or 5 kilohertz. Your audio is not going to be useful above 3 kilohertz anyway, so that's not going to be an issue. On FM, so on the frequency modulation band, for instance, so here's the FM center frequency. This is typical of a repeater, 146.72 megahertz, or 146,720 kilohertz. This signal is 15 kilohertz wide. So it goes down 7.5 and up 7.5. The reason that we do that is because 15 kilohertz above this is another frequency channel. So we don't want to go above that point because then you'll start bleeding into the next channel. What'll happen is receivers aren't designed to receive anything that wide either. So if you are, let's say, making a signal this wide, what will you sound like to somebody who's trying to listen to you if this part of your signal is gone?
Would it be garbled?
It's garbled. Yeah, you'll get distortion. Exactly.
So
So-
by design, we can't really exceed bandwidth.
For the most part, no. So practically speaking, if you're exceeding the bandwidth, for instance, let's say I'm talking into a handheld radio, or I move this mic way too close to my mouth, I'm over deviating. My signal is going too wide. I'm over modulating. And somebody will tell me, hey, you're over modulating. Back off. Similarly, if your signal is not nearly wide enough, let's say it's only this wide, you won't sound very good. And they'll say you need to do more deviation, you need to modulate your signal more. That means you get closer to the microphone. You turn up the microphone gain. So, all these things that we do, they all have practical roots. So, okay, and whoops, I grabbed the wrong thing. Let's grab the right thing. Okay, next thing. Digital modes. We can get through this, then we'll take a short break. Digital modes, packet radio, IEEE 802.11, that's also known as Wi-Fi, and FT8. FT8 is a mode that we heard where you had a whole bunch of signals talking in one single sideband bandwidth at one time. That's FT8. Those are all digital, computer to computer. Packet radio. Packet radio is a digital mode over FM handheld radios, FM modulation. Things that are included, there's a checksum that basically says, looking at data, if I'm supposed to have an even number of ones in my signal. So let's say that I'm sending a word that is supposed to have an even number. So I send 11001111, and then I do a count of those, and I said, oh, there's an odd number, so I add a 1 to the end. That's known as a parity bit. Therefore, when the signal goes through a channel, that being the radio, gets to the other side, the other person hears 10001111 because something got garbled, and they add them up. How many ones are there in there?
5.
Is that an even number or an odd number?
Odd.
And I said it better be an even number, and I'm going to make it an even number. So that's garbage. That's how they would know it's garbage. And the reply would be, oops, please resend it.
Yeah, resend.
Resend. And that's known as an automatic repeat request, or ARQ. So
What modems do.
that's exactly what modems do. That's right. And this is actually a packet modem. Packet radio modem. Okay, next. A header that contains the call sign of the station where it's going. When you send a signal out over into the digital world, you are very often not talking directly to the other person you want to talk to. You're sending a message to somebody. So that message that you're sending out might be handled by 10 different stations along the way. These are known as digipeaters. Instead of repeaters, they're digital repeaters. So this is your addressing information. ARQ, again, I didn't get it. Send it again. APRS, which is the Automated Packet Reporting System. APRS is a system that provides a kind of like a hybrid between radio and global geographic information systems. So if you've ever heard of GIS, GIS is basically mapping of things. So this is APRS in the greater Eugene area. These are all stations. Every little dot you see there is a station that is reporting continually signals over digital packet radio, which is just FM. And these are, for instance, they could be weather. It could be, in some cases, you'll see like this little blue track. That means somebody had it in their car. KJ7CNJ-9 tells you how fast they were going, where they were going. This can be used for tracking weather balloons. It can be used for tracking long-distance, high-altitude balloons. So this is Western Oregon. I can go further out. This is done all over the world. The website for collecting this information is actually in Finland. And when you send out information, it gets collected and put onto the website. So I could look up, let's say, anyone, anywhere who is doing APRS and figure out where they are, how fast they're going, and all their cool stuff like that. If I were to launch a balloon to 30,000 feet, a little helium balloon, and it's floating around in space with a tiny transmitter, which we do by the way, it gets up into the jet stream and blows around for a week, we can track it. It typically has about a 10 milliwatt transmitter, but when it's 30,000 feet up, there's a lot of stations on the ground that can hear it and retransmit its position. And that's again known as APRS. GPS position data, text messages, weather data, etc. PSK is phase shift keying. Okay, somebody mentioned time, let's say the time domain. We talked about time domain a little yesterday. DMR is a time domain multiplexing system for digital voice signals. So, believe it or not, when we're talking right now, you are actually not hearing me. Did you know that? Did everyone know that?
We're hearing reproduction.
And you're not seeing me either. What's happening is that there is a digital representation of my voice, which is being converted into a string of ones and zeros, which is then being handled by my computer, sent over packet switching networks over the internet, and being redistributed as ones and zeros, where it's being reassembled so that I sound like me on your end. That's exactly what DMR is. This is called digital mobile radio. Your voice gets digitized and then split into channel A and channel B so that two different operators can use the same frequency at the same time. Again, that's called DMR. So, all those technologies that exist in the quote real world, they make their way into ham radio as well, and they give you the opportunity to play with it and make it better and develop on it. Okay, WSJTX, this is FT8. In addition to FT8, we do moon bounce with it. We do weak signal propagation beacons, and we do meteor scatter using the same WSJTX package that gives us FT8. FT8 is a very popular digital mode for low signal to noise operations, such as moon bounce. When we talk about moon bounce, we are literally talking about bouncing signals off the moon. And remember, you may remember yesterday I mentioned that, okay, we got a handheld radio with a lousy antenna and a repeater over here with an antenna up in the air. And this might have a path loss of 100 to 150 decibels. Well, if instead of using a repeater, we are trying to bounce a signal off the moon, which has a distance of 250,000 miles. So we have 250,000 miles up and 250,000 miles down. That has a path loss of about minus 225 decibels, which is 0.000000000000000000001 times your original signal strength actually coming back. That's why we use decibels. That's also why we use FT8, because it's a very, very good weak signal mode. This is also why people who do moon bounce might put up a 30-foot wide satellite dish. They might build their own dish. They might have a huge array of antennas to get extra gain, all pointed in the same place at the same time. They might also run a 1500 watt amplifier on both ends, because your signal loss is that much, just due to the distance and the thing that you're bouncing it off of. Okay. Continuing on. Wi-Fi. We do Wi-Fi all the time. Raise your hand if you're using Wi-Fi right now. Everybody, are we using Wi-Fi right now? Almost everybody is.
Yes.
Okay. Wi-Fi is at typically 2.4 or 5.8 gigahertz. What we do is we modify our Wi-Fi radios and we make them smarter, and we develop something called an amateur radio mesh network. One of these kinds of mesh networks is called ARDN, which is the Amateur Radio Emergency Digital Network or Data Network. And what we do is we repurpose old Wi-Fi routers. We bump up their power because we are allowed to, right? We have different power limits that they don't have, so we can bump up their power limits. We can also hook them up to big antennas because they're not allowed to, and we can. We also replace all the firmware. The firmware makes them no longer Wi-Fi routers. It makes them intelligent routers that when they receive a signal, they will figure out what the best path is to get it from point A to point B. Point A to point B might be from Oregon to Idaho. It could be from Oregon to North Dakota. That signal will go from point to point to point to point over Wi-Fi, essentially, at a very high data rate. And that's something that we do, and we're allowed to do. All right, everybody ready for a 5-minute break?
Okay.
All right, excellent. Think of all those questions. All right, rock and roll time. Everybody ready to do this? Okay, we are going back to this. We're into station setup and operating controls. All right, so this is, now that we have all the fundamental math stuff and things like that, we're going to basically look at how to put a station together. All right, first of all, this first question right here, why are short heavy gauge wires used for a transceiver's DC power connection? The answer is to minimize voltage drop when transmitting. What law is this an application of? Everyone.
Ohm's law.
Ohm's law, and which one in particular? E equals I times R. If you have current and you have a resistance, because every wire has resistance, then your voltage drop between your power supply and your radio is going to cause voltage drop. So let's say I have a battery and it's 13.8 volts and it has a plus terminal and a minus terminal, and I hook this up to my radio like this, and it's pulling a current of 10 amps. That 10 amps has to go out and it has to go back. This wire has resistance because every wire, even if it's perfect or almost perfect, has resistance. Which wire is going to have more resistance, this wire or this wire?
Oh, the larger wire.
More resistance.
Yes.
The little wire is going to be more resistant. It's going to have more resistance. The big wire is going to have very low resistance. You want to use, now, here's another one. Which wire is going to have, for the same thickness, which is going to have more resistance?
Okay.
Top one or bottom one?
Bottom one.
Bottom one, because it's physically longer. So when you're connecting a power supply, you want to keep your wires as heavy as you can, gauge wise. You want to keep them as short as you can to lower your voltage drop, because E is equal to I times R. The current is the current necessary to run the radio. Let's say that you have 10 amps and you have half an ohm of resistance. How much voltage drop is there? What's 10 times 0.5?
50.
5 volts.
Oh, four.
Well, let's say you only had 13.8 volts to start with. How many volts are left to run your radio?
8.
8.8 volts. How happy is your equipment going to be?
Unhappy.
Ohm's law. Once again. What percentage of problems are solved by Ohm's law in the real world? 90%. And as Bruce said, probably 95%. Ohm's law, Ohm's law, Ohm's law. Okay, a typical.
Oh, sorry.
Go ahead.
I'm still a little confused. Why is it because the larger wire is more insulated? Because I understand like lengthwise why there would be like if a longer wire has a greater resistance, but I'm still a little bit confused why a skinnier wire would have more resistance.
Okay. What's a wire made of?
Copper line.
Metal.
Copper. Okay. So here's our copper, and here's our copper cross section here. If I'm trying to push 10 amps of current through here, and I'm trying to push 10 amps of current through this one, I have, let's say, 100 centimeters squared, and I have 10 centimeters squared. What's my current density on the top one? 10 amps divided by 100 square centimeters. Down on the bottom one, it's 10 amps per 10 square centimeters. 1 amp per square centimeter. Which of these things am I trying to do more with? Trying to stuff through harder?
Bottom.
The bottom one. It's more resistive. It just has to be. I'm trying to stuff so much more current through every area that it is going to be more resistive.
Did you think about that kind of like a hose with water, like a thin hose versus
Yep.
like a thick hose?
Exactly. The bigger the pipe, the easier it is to push material through it. Does that make sense?
Yes.
Okay, good. All right, let's see. Which is an appropriate power supply rating for a typical 50-watt transmitter? Okay, so our voltage is 13.8 volts. And okay, so we're going to do Ohm's law. What's Ohm's law for power? P is equal to what?
Current.
P is equal to I times
E.
E. Okay. Our battery is 13.8 volts.
E. E.
Our battery is 13.8 volts. Our power is 50 watts. Okay. I'm going to do P, I, E. Which one do we not know?
Current.
Current. So current is P divided by E is 50 divided by 13.8 is about 4 amps. Is that a reasonable number or not? Considering I have a power supply and I have a radio, which is running 50 watts. Is that a reasonable number or not? And to give you a little insight, the answer is 12 amps. So tell me why that's not a reasonable number. Think like a skeptic. Why isn't that a good answer?
You don't have enough current to run the radio.
Sure I do. Well, sort of. Why don't I have enough current to run the radio? Does the radio have lights?
Yeah.
Okay. Okay, so this is part of a system, and this is part of a system. Everything that is required, everything that makes either light or sound or heat or anything that comes out of it, or RF energy, requires energy going in, right? If I have 50 watts of energy going up to an antenna, or 50 watts of power going up to an antenna, and I have, let's say, 2 watts coming out as light, because it's got a backlight, and I've got 5 watts in audio coming out, and let's say 15 watts in heat, and some other stuff. Add all those together, and my 50 watts is not really 50 watts anymore, is it?
On your screen right now.
Right? My 50 watts is not really 50 watts anymore. And has anybody ever seen any piece of electronic equipment that was 100% efficient?
Nope.
Absolutely not. So, in order to make 50 watts of RF requires about 100 watts input power. Typically about 50% efficient. So to make 50 watts of RF energy, you need about 100 watts of input power. Let's do our calculation again, shall we? What's Ohm's law for power?
E equals I over 3.
Come on, what's Ohm's law for power? Somebody speak up.
Electromotive force.
Yes, P equals I times E. Okay. So we know, again, power now is 100 watts. Our voltage is 13.8 volts. So P, I, E. We don't know our current. I is equal to P divided by E is 100 divided by 13.8, which in this case is now about 8 amps. Well, okay, we haven't taken into account lighting and stuff like that, and the power supply choices are typically like 12 amps. That's the next size up. So that's what we would pick, and that's why the answer is 12 amps.
Yeah, so when I said that you only had 4 amps, it wasn't enough to run the system.
It's not enough to run the system, but the question is, why isn't it enough to run the system?
Oh, okay, gotcha.
Okay. Digital mode operation. Okay, so we connect computers to radios all the time. So, how are you hearing me right now? I am speaking into a what?
Microphone.
Okay, and you are listening to me on
Speakers.
speakers. Okay, so if you think of this headset as a radio, my audio, my microphone input is connected to the transmitter, which is the whole system, the computer system that's now going through the internet and coming out on your end into the speakers. Somehow I have to be able to key the transmitter to say I'm transmitting now. In this particular case, it's done automatically. So normally, if I were trying to connect a radio to a computer, you'd have receive audio, transmit audio, and transmitter keying, and those just go back and forth. If I'm running a computer and I'm using the computer as a modem, the modem has to be running on some kind of software. So WSJTX is like a modem software for a bunch of different modes. Okay, so now we're going to just draw something. This is the interface between a radio and a computer. So here's your computer and here's your radio. Your radio normally has a microphone. So there's your microphone, and it also has a speaker. So, if your computer were instead talking to the radio, what would replace the microphone coming out of the computer?
USB connector.
Well, okay. This is a speaker output or line out, and the radio speaker would connect to the microphone line, and then you'd have to have some way of keying the radio. That is known as the PTT, which is push to talk. On a handheld radio, that's the little button on the side. On a microphone, that's a button on the microphone. When I operate, I often use a foot pedal. The foot pedal is the push to talk foot pedal. Okay, what should you use to cure distorted audio? Well, okay. The easiest way to cure distorted audio is using something called a ferrite choke. So yesterday we drew this thing called a transformer. A transformer is a piece of wire wrapped around some kind of iron core. The iron core constrains the magnetic field inside the material. And there's another piece of wire wrapped around the other side, and a current is induced in that other piece of wire by the magnetic field. But sometimes we don't want that magnetic field to go anywhere, and we actually don't do this at all. What we do then is we use a material which constrains the magnetic field on the inside, but then just has it spiral around and around and around until there's nothing left. We typically will do this if we have a combination of audio plus RF energy, because we can do that. So if we were to look at that, we'd have our audio, and then we'd also have our RF energy on that same wire. And we want the audio. So what we want to do is filter out the RF energy. The way we do that is we pick a material that is susceptible to RF energy or RF frequency, radio frequency, magnetic fields, and responds to it by allowing them to circulate. And in the process of doing so, they circulate round and round and round. And what do you think they turn into? Because energy can neither be created nor destroyed. Heat. So what we do is we use this intentionally to convert unwanted frequencies into heat. This is called a toroidal choke. And it's a type of filter. We use that on power supplies. I'll bet if everybody takes a look at a computer power supply, if they have one plugged in, they can find one right now. Let's see who can be the first one to show theirs on the screen. Let's see, hold it up to the screen. Well, that's the power supply, but you're basically looking for what looks like a donut on the cable. You're looking for a donut on your power supply cable. Come on, somebody's got one somewhere. So long as it doesn't disconnect your computer.
Yeah, I don't know how many companies still put those on.
Everybody does.
Ferrite?
Yes. This is called a ferrite choke. There. Okay, there's... Oh, it looks like this. Can everybody see that?
You see that on some of the old DVI cables?
You see that on all kinds of cables. And why are they there? Because
magnetic fields.
Magnetic fields are constrained and burned off as heat in these devices. This separates the DC and the AC in your power supply.
Is there a reason why Mac cables don't have it?
Yeah, it may be that there's one inside. There may be one inside. There may be one in the. It may be that they did some testing and found out that there's enough EMI suppression already that they didn't need it. It also adds some weight.
In here.
What?
On Mac.
It could be built into the power supply there. But I'll say, okay, I'll change it to many power supplies have it now, as opposed to most, because apparently some don't.
I only have like a Baofeng handheld commercial UV82C, so I don't have any idea. It must be built into it somewhere, I guess.
It wouldn't really matter. I mean, there's not going to be one in the power supply because it doesn't really, that radio doesn't care. The power, most charging cables don't care, but if you have really sensitive electronics, like a computer.
Okay.
The problem is has anyone ever experienced what happens if you get radio frequency going into your computer on the power line?
No.
Have anyone ever have a computer just suddenly reboot by itself?
Yes.
I have. That's what happens.
Okay.
So that's why
Windows.
Yeah.
Yes.
I've had computers lock up for that reason, especially in an environment where you're transmitting, let's say, 1,000 watts, and there's RF floating around everywhere. If you don't have RF chokes everywhere, your computer does weird things.
Okay.
All right. Let's see. Another one for bonding RF. So RF bonding. So we were talking yesterday about grounding. Okay. Grounding and bonding. This is like another completely separate discussion. So here's the cross section of a piece of wire. All right. There's a piece of wire. If we were using DC, our current would be evenly distributed throughout the conductor. So that's our DC. If we were using AC at, let's say, 60 hertz, it would be a little bit here, and a little more here, and more toward the outside like this. You'd have nothing in the center. If we were using RF, radio frequency, all of the current, virtually all of it, would be flowing right here. The higher the frequency you go, the more pronounced the effect becomes. This is called the skin effect. And what this leads us to do is, does it matter if a wire's hollow? Not really. You could actually get away with hollow wire, and it would still work. It also does some other weird things because all the current at RF is being carried on the conductor's surface. What it means also is, let's say we want to maximize the amount of surface area where something could be conducted. So we have a piece of copper that's shaped like that. What are some other things we could do to that copper to make it have more surface area?
Flatten it out.
You could make it into a flat strap. That has the same amount of material, but it has a lot more surface area. This is what we use for grounding, believe it or not. The reason we do that is because all the RF current flows on the surface, which means that the current density is a lot lower, which means the resistance is a lot lower at RF for a flat strap than for round. The other interesting thing about this is that okay, here we go. This is our ground. Notice it's nice and green. And we're going to connect our piece of equipment to the safety ground so that if something happens, we won't get a shock. So this is our ground. This is grounded. Does everyone agree that this is power grounded? So far, it's pretty safe, right? Okay. Now, what we're also going to do is we're going to run from this ground what we would call an RF ground. We're going to run it along the same path. And we are operating at, let's say, 10 meters. What voltage is ground at? Everyone.
0.
0 volts. That is our defined 0 volts. I would agree with that. We are operating on the 10-meter band, and this wire is 50 meters long. That wire is 50 meters long. Now, if we were to draw radio frequency waves, if this is at 0 volts, how many volts is it at right there? Not a trick question. It's at 0. Where on this graph am I at 0? Right at the end. Well, what did I say the wavelength was? 10 meters. So every 10 meters, my voltage actually does this. So if I look at different points along that, quote, ground wire, am I always at 0 volts?
No.
This is messed up, isn't it?
Yeah.
Any piece of wire, first of all, if it's carrying voltage and current, what does it turn into?
Resistor.
No?
An antenna.
That turns into an antenna, an unintentional antenna. And on top of that, what if you happen to end this wire at a high voltage point and you're transmitting and you touch the cabinet?
You get a shock.
You'll get a shock. That's right. Now, it'll be a radio frequency shock. and it might poke a hole in your skin. That would be the source of an RF burn. So our goal when we're doing grounding, there's a difference between safety ground
RF ground.
and RF ground. This is our safety ground, and this is our RF ground. They are completely different things. So, how do you think we make our RF ground work as best as we can?
Short as possible.
Make it really, really short. Now, if you happen to live on the second floor, that might not be so easy. Doesn't mean you shouldn't try, but if you live down on the ground floor, your safety ground is different from your RF ground. You know, you can use a cold water pipe for the safety ground, but if you've got a 50-foot run to get to that ground point, you probably want to put another ground rod in the ground for your earth ground for your RF. Okay. If you're putting a radio in a car,
I got a question.
Yes.
Putting a tower up, say it's going to be 70, 80 feet from where our radio station is going to be.
Mm-hmm.
And I plan on grounding the tower
Yep.
with 3 grounding rods.
Yep.
But do I need to put another grounding rod right next to the house where the radio is going to be?
I would.
To the short distance for that
I would.
RF ground?
I
Okay.
would. And in
All
fact, so if you're putting up a tower, here's your 3-legged tower,
Mm-hmm.
right? You have
Yeah.
a ground rod and a ground rod and a ground rod.
Yeah,
That
and you
goes
got
here,
your-
that goes here,
yeah.
that goes here, and then it goes all the way around.
Mm-hmm.
Then you have it coming here. There's another ground rod where it enters the house. And then on top of that, let's say you have your antenna here. Your antenna is going to come down through here. There's going to be a suppressor right here, which is going to be bolted to the ground, bolted to that ground right
Mhm.
there. So that what happens is this is a gas-filled tube. If you get a very high voltage that hits the antenna, it'll ionize the material, the gas in the tube, and instead of going this way, it will now go this way.
Uh-huh.
And so all your equipment also gets grounded to that rod. And this is all actually defined by National Electric Code as well as your local codes.
Okay.
So
Thank you.
here's another question. If you're doing a ground rod, why should you always either bolt it or weld it and not solder it?
Oh.
Different types of materials.
Nope.
A lot of breaks down over time.
Oh, nope.
Solder.
If you get 20,000 volts at current,
And melt the solder.
it'll melt the solder, and then you won't have ground anymore. That's why we don't use solder.
So could you use a bus bar?
You could use a bus bar. You can bolt it to a bus bar. We also use something called CAD weld. If anyone's familiar with CAD weld, it's basically thermite,
Yeah.
where it melts steel and welds everything together.
Yeah. Watch
They
them.
do that with railroad tracks.
That's
Yeah.
exactly right.
Watch them weld railroad tracks.
That's exactly the same thing we do. Okay. How do you determine the amount of oh, here we go. Car batteries. So we're talking more about power connections. Why do you go back to the battery ground on the battery itself? As opposed to, if you look at how a car electrical system is built, ground is considered the frame of the vehicle. So here's the car. God, it's an ugly car. The entire frame of the car, every point on the car, is considered ground. So if I have a battery and here's the plus, let's say I want to go to a light, the light's back here, and the other side of the light, they just tie to the ground of the car. If you're doing a radio system, why don't you do that?
The RF signal.
No, it's all about DC power. What is this all assuming is true? This all assumes that the frame of the car is suitable for a return path for, let's say, 20 amps. That means you have to have 20 amps that gets back to the battery. You are assuming that the car itself, the frame of the car, is suitable for carrying 20 amps, when in fact, I don't know if it is. So instead what we do is we run this directly back to the battery. Don't want to make assumptions like that. How do we decide whether or not a battery is big enough to do the job? And for what period of time? Batteries are rated by something called either amp hours or watt hours. An amp hour rating is, for instance, 120 amp hours. It'll be specified at, let's say, 5 amps. So if it's 120 amp hours, you could draw 5 amps for 24 hours. Just basically multiply them together to get the rating. Conceivably, you could also draw 1 amp for 120 hours. Sometimes they'll say watt hours. What is a watt again? Power is equal to volts times amps, because P is equal to I times E. So sometimes when they specify something in watt hours, that means that it can deliver, let's say, 1200 watt hours, and it's a 12 volt battery. That means it's good for 100 amp hours. And then you go through the same calculations to figure out how long it's good for. Operating controls. My excessive microphone gain basically does this. It'll sound all distorted. Tuning an FM receiver above or below a signal's frequency will distort the signal's audio. The same thing is true on single sideband. What can be used to enter a transceiver's operating frequency? That would be the knob, the tuning knob. How to access a favorite frequency? You store it in a memory channel. My single simple handheld has 1,000 memories built into it. So I can basically program them in banks. If I'm traveling, I can program an entire bank of frequencies just for my trip. The purpose of a squelch function. Basically, a squelch. Let me go back to a web SDR. This is a good thing to have. The squelch function mutes the receiver when there's nothing interesting to listen to. If you're like my wife and she doesn't like listening to static, the squelch is a great thing. I don't mind listening to static. I leave my squelch open usually. How is squelch adjusted so that a weak FM signal can be heard? Every Saturday, we do something called the simplex net here in Eugene, where you're never really expecting somebody to be a super strong signal. You turn your squelch all the way off so that you can hear noise, and that if there's a weak signal in there, it breaks through just a little bit. Okay, now we're into how repeaters work. Okay, so there's a couple of things about a repeater. What is a repeater? Somebody tell me what a repeater is.
That's something that sends signals forward.
Okay, what is it? Where does it get them in the first place?
From your transmitter.
Yes. Okay, so here's me, accurately drawn, with my handheld radio. Here's a repeater. The repeater inside has a transmitter and a receiver and a controller. It also has some filters. Okay, so these are connected together. These are connected like that. Okay, when I transmit a signal up into the repeater hears me on one frequency and then retransmits my signal everywhere. And the reason for doing this is that if it can hear me, and other people can hear it, then it sounds as though people can hear me. Similarly, if I draw another person over here who's on the other side of a mountaintop with another handheld, and that person can be heard by the repeater, that signal can also be retransmitted. So that makes us able to have mutual communications with each other from opposite sides of a mountaintop, which is great because if we tried to transmit directly to each other for a long distance, we would not be able to. This is where repeaters really shine. Now, a repeater's published frequency will be its transmitting frequency. In this case, I'm going to pick our local repeater and say that it's 146.72 megahertz. This is on the 2-meter band. By convention, this receiver's input frequency is 146.12 megahertz, which means that the repeater offset is negative 0.6 megahertz, or 600 kilohertz. That's known as its offset. The offset distance is how far off it is. Notice the direction is negative. Depending on the repeater, depending on where it is, depending on the frequency it is, that also could be positive. It's basically telling you what frequency you need to transmit on to be heard. That is the offset. Now, there are a couple other things that a repeater can do. One thing is that it can require you to transmit what's known as a CTCSS. CTCSS. This is a subaudible tone between 67 and 254 hertz, which is low frequency. It requires you, kind of like having a key, to be transmitting that along with your voice in order to have that signal get into the controller. The signal comes down like this, goes through filters, goes into the receiver, then into the controller to be evaluated to say, is that key there? If the key is there, it will then send your signal out to the transmitter and back out to the antenna where it can be retransmitted. If that signal is not there, it will not be retransmitted. There's also something called DCS, which is a frequency jumping mechanism by which your signal is shifted in a discernible pattern by just a little bit. If the controller does not hear that slight change on a periodic basis, as it's supposed to do, it will reject your signal as well and not retransmit it. So there we go. This is basically how a repeater system works. Now, one thing that's interesting about this is that what is the offset right here? How many kilohertz? In this case, it's 600 kilohertz. Is it possible for me to use the same antenna for receiving and transmitting? What do you think?
Yes.
Okay, and what's one of the pitfalls of that? These frequencies are really close together. What's one of the pitfalls of that? If I transmit with myself, if I transmit too close in frequency, I transmit a little bit, remembering that this repeater might be transmitting 100 watts going out. How strong does the signal have to be to activate the repeater? On the order of 0.0000000000001 watt. In other words, of that 100 watts, I'm a little bit off frequency, but I only need this much incident energy that's sneaking through to make this repeater lock up, where my transmitted signal, enough of it comes back that it goes through and it just ends up in a loop and doesn't work anymore. How do I make it so that that 100 watts on a slightly different frequency is then cleaned up so I don't even get that much power back in?
I have no idea. No idea.
I just put a big yellow circle around it.
Filter.
Filters, filters, filters. A series of filters for a repeater like this might have 130 decibels of isolation. And what does 130 decibels mean? 10 to the what?
1,000.
10 to the minus 13. So 0.0000000000001 times. This is not a cheap filter. This is not an easily made filter. This filter typically looks like something like this. Remember, what are filters usually made of? There are two elements that make up filters.
Wire and a core.
Yeah, but there are two elements that make up filters: capacitors and
Oh, resistance.
no. What are the two components? Capacitors and inductors. Okay. Repeater filter canisters. This is what. Not that. Yes, yes, yes. Move on. Keep going. Keep going. Keep going. That is a single repeater system, a single filter system for a single repeater.
Can you show your
Can
screen?
you show it to us?
Oh, there we go. Darn it! I didn't hit send. Okay. There we go. That is a single filter system for one repeater,
Wow.
so that the output does not get back into the input. Notice all the cables. Notice those cans. Those cans are actually tuned cavities. So a system like this is why people don't generally build repeaters on their own. Because that series of filters might cost itself $5,000.
Oh,
Well, they're precision built, you know. They're precision built. They require special tuning. That's why most repeater systems, when you start dealing with that, are put up by clubs, because they can afford, you know, collectively to do something like that.
they must have a big club.
Okay. What function is performed with a transceiver and a digital mode hotspot? That would be communication using digital voice or data systems over the internet. We also call this voice over internet protocol, or VoIP or VoIP. If anyone is curious, our repeater here in Eugene for the Valley Club, it is actually on Echolink and Allstar, which are two modes of allowing a repeater system to be tied to the internet. We have people check in, like myself, from all over the world when they're traveling. So it's a link between RF and the internet. A talk group is on a digital repeater is a way for multiple people to share a channel at the same time without hearing each other. You enter a talk group by using the group ID or code. A digital mobile radio code plug contains all the information for repeaters and talk groups in a given area. Now, interestingly, because DMR can access the internet, a DMR radio might have 200,000 different repeaters programmed in, because it's not just the ones in your local area, it's the ones in your local area plus every other one that's on the web, which you can access as though it were local if you have an internet connection. Pretty amazing. How is a specific group of stations selected on a digital voice transceiver? By entering the group's ID code. Again, the color code must match the repeater color code. It's like another level of security. D-Star is an ICOM and Kenwood thing. If you start looking at companies, you must program your call sign in before using it. If you're using a multi-mode transceiver, multi-mode means not just FM, but single sideband, Morse code, etc., etc. Having multiple receive bandwidth choices, we listened to that a little bit, permits noise or interference reduction by selecting an appropriate bandwidth. For single sideband, 2.4 kilohertz. For Morse code, it's about 500 hertz. It can be even narrower than that. If your voice pitch of a single sideband is too high or too low, that would mean you use the RIT. You could also just change the frequency. The push to talk button keys the transmitter, switches it from receive to transmit. Now we're into station equipment. A transceiver, that's a portmanteau of the words transmitter and receiver, combination of the two. A transverter converts one frequency to another band. So there's a device called a mixer, which is not what we think of when we think of like a stereo mixer. A mixer takes one frequency, combines it with another frequency, and produces F1 plus F2, F1 minus F2, F2 minus F1, 2 times F1, 2 times F2, and a whole bunch of other ridiculous stuff. This has some very positive benefits as well. If I were to mix 194 megahertz with 28, one of the things that I get out is the add of the two of them, which is 222. And if we look at our frequency chart, we'll see that 222 is in the 1.25 meter band. This is known as a transverter. And the core of a transverter is a mixer. But because we also have all of these different other frequencies that come out, for instance, we have 384, we have 56, we have the difference, which would be 166, we have F1 minus F2, we have something negative. How do we get rid of all those ones that we don't want and just select the one that we do want? What would you build? This is like your final exam. What would you build to make sure that you only get the one that you want? What would that be? Starts with the letter F.
Filter.
A filter. This is your filter, and it would be a bandpass filter. Filters, filters, filters. They show up everywhere. They're all around you all the time. Anything that has a tuning, anything that selects a frequency, filters, filters, filters. My wife says I have a selective hearing filter as well. Anyone else have that?
Yes.
Yeah. Okay, a device that increases transmitted output power is an RF power amplifier. The reason that we have on an SSB and CW-FM switch on a VHF power amplifier sets it in the proper mode of operation. Okay, so I'm going to flash back to a long time ago now, which was yesterday, and ask if anyone remembers what this thing is called.
Transistor.
Transistor. And in fact, it's called a bipolar junction transistor. This is the base, this is the collector, and this is the emitter of this bipolar junction transistor. Okay, so on this transistor, what we have is a curve of input and output where it looks like this. It has three regions. This is linear. And again, this is cutoff when it's first turning on. And this is saturation up here. CW and FM use this region and this region. Single sideband, because voice wants to be amplified linearly to keep it from getting all distorted, uses this right here. And that's why we have two different modes of operation for every amplifier. Using the wrong one will either cause distortion or be wasteful of power. Okay. All right. Okay, everybody unmute yourself. Right? Everyone unmute yourself. We're going to do a little experiment. Okay. Okay. Now the question is, can everybody hear what I'm saying?
Yeah.
Could everybody hear that?
Mm-hmm.
Okay. Well, okay, that is called sensitivity. Your ability to hear weak signals. Now, ready? Everybody on the count of three, say your name. Ready? 1, 2, 3.
Dan,
Understood.
If you could pick one of those voices out, that would be selectivity. That's the definition of selectivity. Okay. To improve the sensitivity of a receiver, you install something called an RF preamplifier. You want to put a preamplifier up near the antenna. So what a preamplifier does is, here's your receiver. Here's your antenna. And what we're going to do now is look at systems again and say that your signal that you're receiving, in order to hear it at all, has to be minus 120 dBm, which is decibels compared to a milliwatt. If it is below that, you hear nothing. If it's above that, you hear something. The signal that's coming through space has a signal strength of minus 130 dBm. This antenna that you've put up has a gain of plus 15 dB. The cable that you have has a loss of minus 10 dB. Will you hear the signal or not?
Yes.
Well, let's go through. Minus 130 plus 15 is minus 115.
Right.
Minus 10 is minus 125. Want to change your answer there?
yeah, no, you can't
Because
hear.
now 125 is below the threshold.
Okay.
Okay, so here's a question. If I put a preamplifier on, which has a noise, it has a minimum discernible noise signal of 120 dBm, just like the receiver, but it has a gain of plus 10 dB, will that help me if I put it there?
Yes.
It will not, because right here, I still have minus 125.
Oh,
But what I can do is instead, I can take it and I can put it way up here.
okay.
And I can add that plus 10 again. So now, right here at the base of the antenna, I have minus 115. This thing is good at hearing down to minus 120. So the answer is yes. Now I'm at minus 105. I subtract minus 10. By the time I get down here, I'm at minus 115. And all of a sudden I can hear the signal. So where you put a preamplifier is very, very important. Has anyone ever experienced this with their cable company? Signal's not strong enough, so they go put a preamplifier somewhere. Depending on where they put it, it might actually help or not. It's a lot easier to amplify something when you can still hear it than once it's gone.
Yeah, but you can also add distortions or.
That's true.
Yeah.
But if you have no choice, if you have to add something, that's where you put it. You put it as close to the antenna as possible.
Can you add two up there by the antenna so it would boost it even more?
Sure. Yeah, you can add a bigger one. So long as they have low noise figure, you can add multiple. Now, at some point, it might not be useful to do so, or you could add a single one with higher gain. It just depends how you want to design it. Okay. To convert one signal from one frequency to another, you use a mixer. How do you generate a frequency? You use something called an oscillator. It oscillates. You used to, on the novice exam, you used to have to draw oscillators. You don't have to do that anymore. They would say, draw a Colpitts oscillator, and your examiner would go over it with a fine-tooth comb and see if you did it right. Which of the following describes combining speech with an RF signal? That would be modulation. And now we're into things that go wrong. What can cause RFI? Radio frequency interference. Fundamental overload, just too much signal. Harmonics, we covered harmonics. And spurious emissions, which are signals that are sent out when there's no need for them to be sent out on a frequency that you never planned. A neighbor tells you that your station is interfering with their TV or radio. If your station first is functioning properly and it doesn't interfere with your own radio or TV, then the problem is on their side. Are you required to fix it? The answer is no. Now, as a neighbor, you might want to help. If you have non-fiber optic TV, you may have noticed that your connectors tend to loosen just spontaneously for no good reason. If you're getting interfered with, go tight, make sure all the connectors are tight. A broadcast AM or FM radio can receive ham radio transmissions. My parents' stereo used to hear this. What was funny was it even did that when the stereo was turned off. They would actually hear me. They could tell when I was on the air because even with the stereo off, and it was all distorted, but they could tell. So the receiver is unable to reject strong signals outside the band. So that's a problem with the receiver. How can fundamental overload of a non-amateur radio or TV receiver be reduced or eliminated? See that word again? See how that's showing up everywhere? Filter, 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 filter. It allows you to reject frequencies you don't want and select the ones that you do. Notice this one. What can reduce overload of a VHF transceiver by a nearby FM station? Installing a band reject filter. Filters, filters, filters. What are the two things that make up most filters? Two components.
Inductor and a capacitor.
Inductor and capacitor. It's like magic. What do you do if something in your neighbor's house is causing harmful interference? Work with your neighbor to find it. Inform your neighbor that if the FCC rules prohibit the use of devices that do that, and make sure that everything in your station has been built properly. So, does everybody have time, you think, for like a 1-minute story? That's a great story, I think.
Sure.
Okay. So, this actually happened to me. I was on the 80 meter band, which was 3.5 megahertz, and I heard on FM modulation somebody talking. And then it would be replaced with a dial tone, and then it would go away. And then I'd hear it again. And then sometimes it would be a dial tone, and sometimes it would just be a blank carrier. I'm like, well, that sounds like a phone. I walked around my neighborhood. I did this for a period of 2 years. Eventually, I tracked it down to one house, who it turned out my wife actually knew the person who lived there. And I said, could you give her a call while I'm listening? And I heard them talking on my radio, on the ham radio. It turned out that what they had was something that plugged into with a phone jack and the power lines, and used the power lines to expand the phone lines around the house, so that in different places in the house, all they had to do was plug into the phone jack to the power jack, and they could use the phone. Not realizing that at the same time, the frequency that was being used and the wiring in the house turned it into a giant neighborhood antenna. And they were literally broadcasting their phone calls all around the neighborhood. At which point I told her what it was doing, and she said, I don't want to do that. It's like, no, you probably don't. So at which point she unplugged it and said, here, take it. Make it so it never works again. So she gave it to me, and I gave it to a friend of mine who specifically worked with radio frequency interference, and he was thrilled to get it, and we were happy to get it off the air. And they were happy to never use it again. So,
was it a Cobra?
I don't remember. It could have been a Cobra or a Uniden or something.
Cobra did that to me.
Did they? Yeah. I mean, it's a great device, but yeah. A symptom of RF feedback or unintelligibility. If your transmitter's off frequency, your batteries are low, you're in a bad spot. If you have RF feedback can basically sound like this. It's basically radio frequency getting into your microphone. And if you're over deviating, that means your signal is getting too wide. Handheld radios typically don't have microphone gain controls, so they typically tell you to back away. Okay, basic instruments, test instruments, and soldering and stuff like that. So here's a multimeter. Here's what a multimeter does. Let's say I have a power supply that looks like this. And I want to take my voltmeter and see what is coming out. Here's the plus, here's the minus. That's how a voltmeter would work. A voltmeter measures voltage. Now, let's say I have a current flowing. I want to measure it. I have a plus and a minus. That is an ammeter. It measures current. It has to be in line with, unless it's inductive, it has to be in line with the circuit. Now, there's also something called an ohm meter, which allows me to measure resistance. Now, an ohm meter internally looks like this. It has a voltmeter and an ammeter, and it connects up to the mystery resistor. Interesting, right? So how is this actually telling me what the resistance is? This is using Ohm's law. When you use an ohm meter, it is using Ohm's law to say that E equals I times R. So therefore R is equal to E divided by I. It's measuring your E right here. It's measuring your I right here. When you hook it up, it tells you by calculating it what the resistance is. So the pitfall, of course, is that if I wanted to measure this resistor right here, and essentially my ohm meter has an ohm meter, it has a power supply built into it, and I hook it across right here, what will happen is I will blow up my ohm meter if I'm unlucky. Because this has all the current coming out of the battery that already exists, going right through my meter. So in order to measure this properly, you never want to use an ohm meter to measure something that is in an existing circuit. So what you would do is you would take it out of the circuit or break the circuit in order to take your test. And that's an ohm meter. And yes, I have actually popped fuses and blown up meters and stuff like that. The more things you do, the more things you'll do wrong. Just the way things are. We learn from our mistakes. Okay, voltmeter is in parallel, an ammeter is in series. Don't try to measure voltage when using the resistance setting or vice versa. When you're measuring something, when you're measuring a voltage, make sure that the meter is rated for the proper voltage. So I'm going to bring up 2 meters here. Okay, here we go. I'm going to bring up pictures of 2 meters, a tail of 2 voltmeters. Okay, so can everybody see this meter? Everyone have a Harbor Freight near them?
Yeah.
Harbor Freight's great, right? This is a $9 meter, right? I can also go here and take a look at this. Does everyone see this? My Fluke 85, my Fluke 87 for $470.
Mm-hmm.
This meter is just fine for measuring 24 volts, maybe 120 volts. I don't know if the board is really suitable for it. Notice it's rated 250 volts. Personally, I would never really use it for that. However, I have one of these for work. This goes to work with me in the field. I know the leads are rated for 1,000 volts. I know that the meter is rated for 1,000 volts. And okay, it's $470. But if I'm measuring something that's 480 volts or even 240 volts, I don't want something to blow up in my hands. So your selection of a meter, make sure it's rated for the proper voltage and be smart about it because you don't want to have something blow up. Okay. If you connect a circuit with an ohm meter, if you're measuring resistance and you are looking at a circuit and you see that it looks like a short circuit, but then slowly it looks like an open circuit, what's happening is that you are charging a capacitor using the battery in the meter. It's a way to tell that, let's say you're hooking it up to a power supply. To measure current, again, that's an ammeter. It's put in series. There are multiple different kinds of solder out there. The only kind of solder that we use for electronic soldering is something called rosin core. We do not use acid core. Acid core is used for plumbing.
What about silver solder?
Silver solder is okay too. Basically lead, tin, silver, copper, they'll typically all have a rosin core. Okay. Unless, of course, you're using a torch, in which case I think you probably still use rosin. A cold tin and lead solder joint. Now, what would be a reason to not use lead in your solder?
Because it would
You-
heat up and melt.
The fumes?
The fumes, yeah.
Yeah.
That when the rosin burns off, it carries a little bit of lead with it. I've probably been guilty of this many times. You try to do it in a well ventilated area so you don't get a face full of lead fumes. Also, when you're done soldering, what do? You never smoke, and you always wash your hands before eating, just so you don't eat lead. A cold solder joint looks like bumpy and lumpy. Okay, so now we're into FM operating procedures. And let's see if we're into FM operating procedures. A repeater retransmits a signal. A signal that can automatically retransmit the signal of another signal is a repeater, auxiliary, or space station. Okay, a repeater is a repeater, just like we think of. An auxiliary station is like a forwarding system that it's not really expected to be heard, but it can be used to connect two radios together. A space station is anything 50 kilometers up or higher. Any of those can automatically retransmit signals. In other words, like satellites. A linked repeater system is one where one repeater is connected to another through a backbone, either over the internet or over RF links. Common frequency offsets. In the 2 meter band, this is just memorization, plus or minus 600 kilohertz. In the 70 centimeter band, it's plus or minus 5 megahertz. CTCSS, again, is that extra special key that gets sent along with your transmission. When it's received by, if it's the proper one and it's received by the repeater, it will allow your signal to be retransmitted. If you can't access a repeater, you might have the wrong offset. Let's say it's plus and you have minus programmed into your radio. If you don't have the right tone, or if you don't have the right DCS code, which is that little frequency hopping thing, your signal will be rejected. The reverse function, normally, if I would be transmitting on 146.72, if I would be on a 146.72 repeater, my transmitted signal would be 146.12. Reverse allows me to swap so that I can listen to the transmitting signal for other people who are transmitting. It might turn out that there's somebody really close to me who is using the repeater and is really noisy into the repeater, but I can hear them just fine. So that's a way of telling that you can do that. It's called using the reverse, it's called using the reverse frequency. On voice peaks, if your FM transmission is distorted, it's the same thing as doing this. Okay, I can fix that by talking quieter. I can also back off from the microphone. To call another station. Okay, who here's got their license already? Anyone? Toto.
I do have it.
What's your call, Toto?
K7 ASP.
Kilo 7 Alpha Sierra Papa. This is November 7 Juliet India. Over.
Yes. Hello, Kilo. Hello. I didn't hear your call sign. Sorry.
November 7 Juliet India. How would you answer me?
Hello, N7 Julia. Could you repeat it?
November 7 Juliet India.
Hello, N7 Julia India. This is K7 ASP.
K7 ASP. This is N7JI. How are you doing this morning, Toto?
I'm doing great. How about you?
Oh, doing fine. Just teaching a class, having a lot of fun.
That's great to hear.
How's school been for you?
It's been great. Yep.
And notice we're not using our call signs right now, right? Well, that's good. I got to go back to teaching a class. K7 ASP, N7JI. Talk to you later.
Okay, great. K7 NJ7 N7JI K7 ASP. Great to see you.
Okay, so to talk to somebody else, you give their call sign and then your call sign. Hey, Bob, this is Scott. Can you hear me? Just replace those with call signs. If I just want to say that I'm listening on a frequency, November 7, Juliet, India, monitoring or listening. When we're on the same frequency, like Toto and I just were, that would be known as simplex. Why are there simplex channels? Because a repeater is a resource. And sometimes you're so close to somebody else that there's no point tying up that resource. So, unless you really want other people to hear what you're talking about and to join into a conversation, you just use simplex. In addition, there is something called the National Simplex Calling Frequency on FM, 146.52. This is in pretty much all of North America. This frequency is almost always monitored by anyone who's scanning. So you're driving through some area where it doesn't look like there are any hams. You make a call on 146.52. You stand a fair chance of finding somebody. HF operation. CQ. CQ, we use it on VHF also, just not typically on repeaters. CQ means I'm looking for anyone to talk to. And what do you do before calling CQ? Well, you listen, listen, listen. You make sure that you're allowed to be there. And how do you make sure that you're allowed to be there? You've got this handy dandy frequency chart. You will know by looking at this, if you have a technician license, where you're allowed to be. If you have a general license, you'll replace the T with the letter G. If you have an extra class license, you'll be looking at the letter E. If you have an A class license, which is advanced, then you've had your license for over 20-something years because they haven't assigned them in over 20 years. Okay, knowing how to call CQ is important. Knowing how to accept it. How do you respond to a station calling CQ? Toto, are you ready?
Yep, I'm ready.
CQ, CQ, CQ. November 7, Juliet, India, Eugene, Oregon, calling CQ and listening.
Hello, November 7 Juliet, India. This is K7 ASP, Kilo 7 Alpha Sierra Papa, in Oregon, Scio, Oregon. How are you doing?
Very good. Thank you for the call, Toto. K7ASP, 59, and I'm going to get back to teaching my class. Just give me your report, and then I got to run, okay?
Great. This is K7 ASP. I hear the signal great. It's around, 5-9, and have a great day.
All right, thanks. K7ASP, 73, N7JI. Okay, so how do you answer? You give their call sign, then you give your own. When do you have to identify? You have to identify whenever you make a transmission.
Quick question.
Yes.
What was the 5-9?
That is a signal report.
Huh, okay.
So we will get to that very shortly. An on-air test transmission. Basically, the rule is that you have to identify every 10 minutes and at the end of your communications. If you're making a test transmission, the easiest way to make sure that it's identified is by sending your call sign. You send your call sign, you're done. QRM, we use Q signals out the wazoo on HF. Sometimes we use them on VHF as well. QRM means I'm receiving interference. QRN means I'm receiving natural noise interference, like static crashes. QSY means we're going to change frequency. So, and we use Q signals because on Morse code, they really save a lot of time. A band plan. This is a band plan. The FCC does not dictate this band plan. This is something that is done as an agreement to keep the peace and make sure that we don't have just total chaos on the bands. One thing that hams are usually really good at is self-policing. People will follow the band plan because nobody wants to create almost nobody wants to create chaos, and even fewer people want to be affected by chaos. So, a band plan is a voluntary guideline for establishing what modes get used where. Basic tentative radio is to operate courteously. When two stations are on the band, at the same time on the same frequency, who owns the frequency? And the answer is nobody owns the frequency. So they'll decide, let's say that I'm in the middle of a conversation and somebody says, is the frequency in use? And I say, yes, it is. And they'll say, well, we're starting a net here in 3 minutes, and we've got people from 47 states checking in. Would it be okay if you moved and we stay here? Okay, so then you get into negotiation. Nobody owns a frequency. Okay, public service. Amateur radio emergency service is a volunteer service where hams have registered their qualifications and equipment for communications duty in the public service. This is very similar to RACES, which is the Radio Amateur Civil Emergency Service. Amateur Radio Emergency Service, Radio Amateur Civil Emergency Service. The only difference is that word civil. RACES is for civil defense, which means that it's governmental. ARES is administered by the American Radio Relay League and is a volunteer effort with state governments. RACES is actually run by the state government. A net control station, if we are operating a net is short for network. It's typically either an ad hoc network or it can be something that is scripted and occurs every day. The net control station is the traffic cop. That's basically what the net control station is. They start the net, they end the net, they look for people checking in, and they are the traffic cop, controlling traffic being information that passes from one person to another. When you participate in a net, your job is to basically not talk unless you're spoken to and asked to talk. Because, again, frequency and available time is a resource. If you're on a net, the intent is that you are participating in a network of people who are there to help something along. And if you're busy talking about whatever, that means that somebody else who might have more important information can't talk at the same time. You don't have multiple frequencies to use. Traffic is messages exchanged. Good traffic handling means you don't make any mistakes. That means that if there's a word count of your message, you say, I am going to the zoo. 1, 2, 3, 4, 5, 6. And you say, my word count was 7. And somebody gets that and says, I am going to the zoo. Wait, that's only 6. Wait, there's something missing. The word that might have been missing was not. It got lost. So they say, okay, I need a repeat. You say, I am not going to the zoo. 7. Said, okay, that makes sense now. So that's actually, that's the kind of stuff that we'll do on nets, making sure that information gets to the endpoint perfectly. So let's say that my last name is Kalnitz, right? I can think of a couple different ways that somebody might spell Kalnitz. It's not Jones. It's not Smith. So if I want somebody, let's say I'm passing information and it's about Bruce Kalnitz. And I would say Bruce Kalnitz. I spell Kilo Alpha Lima November India Tango Zulu. I would use phonetics to take care of anything that was not something that somebody might just get the first time. And I would use the International Phonetic Alphabet. The preamble, again, the preamble is information needed to track the message. The check, again, is the number of words or word equivalents, which we just did. Which doesn't apply to the operation of an amateur station. And see, this is the part of this class that is just like rules and regs that you just got to go over. When do the FCC rules not apply? And the answer is the rules always apply. Now, when do the rules not apply? Then the rules are typically that we're not allowed to do certain things, like operate outside of our frequency privileges, or outside of a ham band if we have a ham license. If we have immediate safety of human life or protection of property, then you're allowed to do that. You might have to explain and show that there really was no other way. There was somebody recently who, during a wildfire, decided he was going to get on the fire frequencies and tell the wildland firefighters where the fire was, he could have just as easily picked up the phone. He got fined $34,000 for that. So it's serious, you know. If if there's if there's truly no other way, nobody's going to question you. But if there's another way, you should use it. Okay, amateur satellites. Satellites are things that fly up in space, 50 miles up or 50 kilometers up or higher. Who can contact the International Space Station? If you have a technician class or higher and you're allowed to be there, you can do that. A satellite operating in UV mode, that's uplink in UHF, downlink in VHF. Typically this U is 70 centimeters and the V is 2 meters. Transmission modes, transmissions that are often sent by satellites, single sideband, FM, Morse code. They do them all. On a satellite uplink, if you transmit with too much power, you can block other users from accessing it. You're essentially overwhelming the receiver. If you listen to, and you would think that you would be able to hear a satellite going beep, beep, beep on the downlink before you try to transmit to it. If it can be heard, the satellite sends out a beacon, which is the beep, beep, beep. It might also be health. It might be status of the satellite. It could be altitude, weather, up in space. If your voice is about the same loudness as the beacon, then you're about the right strength. LEO is low Earth orbit. That's what LEO means. No offense to anyone named Leo, but that's what LEO means. A satellite beacon, again, contains information about the satellite. Telemetry information, that contains health and status of the satellite, and anyone can receive satellite information. You do not need a ham license to receive. Satellite tracking programs. Well, a satellite tracking program will actually show where a particular satellite is at any point over the Earth. A satellite's orbit, and in fact any orbit, is determined by its Keplerian elements, named after Johannes Kepler. When dealing with satellites, because satellites are moving very, very fast unless they're geostationary, with respect to the Earth, they're moving at up to 17,000 miles an hour. We don't usually think of Doppler effect. The Doppler is what you hear when a fire truck goes by. And the pitch changes. Well, it turns out that the reason that that's true is because the speed of a fire truck or a police car is close enough. It's actually significant when compared to the speed of sound. But in normal life, we don't have to worry about that when compared to the speed of light. However, when a satellite is moving at 17,000 miles an hour, we actually do have to. And we actually have to consider Doppler effect and change our frequencies a little bit when talking to a satellite. And finally, when dealing with satellites, satellites tumble in orbit. They don't just sit there. Their antennas are on typically one side of the satellite, and as the satellite goes and spins, the antennas might disappear from view. So that's known as spin fading. And how about a 10-minute break?
Sounds
Does that
good.
work? Good, okay.
Dale? Yes. Oh, scared me. Time. Was last time I came out. Oh, did you think I was still in it from earlier? The product that you bought, is that the crochet? I mean, I did it. Yes. I'm sorry. I'm sorry. Oh, that would have been awful. Then I would have been dead, huh? Oh, I don't think that would be a good thing. It's supposed to rain. Going out today. Get my hair washed.
I'm gonna dabble in some SDR.
Oh, there we go. I've got one of those.
Yeah.
The new elect ones.
Yeah.
I
also
have
the ham band.
So what are you using for the software? You have SDR Sharp or?
I don't know. I'm thinking about setting up a Linux station. There's the GNU radio software.
Oh my God, you're gonna have so much fun with this stuff. You know that, right?
Yeah. Well,
I mean, this is such a big and continually developing world of this area.
Have you heard of ACES?
Yeah.
Okay. It's kind of like that, races and.
Mm-hmm.
But there's training in Oregon and Washington State.
Yep. Now there's Aces, Races, Aries, Oxcom, and the big change in the last year or two is that, you know, I probably mentioned I'm the ARRL Oregon section manager, and
Oh no, yeah,
and Aries and the MCOM stuff all falls under me.
oh cool.
And I knew almost nothing about it until I needed to, and now I feel like I almost know too much about it. But we work with the State Department of Department of Emergency Management,
Right.
and so all of those aforementioned groups, and basically anybody who does MCOM, is now really considered part of, we need your help.
Right.
So
yeah, it's one of the things. I don't know if are you a cert?
I'm a cert too. Yeah.
Yeah. So everything's premised on there's going to be all the emergency services are going to be overwhelmed.
That's right.
And you're going to have to be self-dependent.
Well, and even if we're only handling some backbone traffic information, I mean, health and welfare is really significant. If somebody just wants to tell somebody, hey, you know what, I'm not dead.
Right.
That's information. That's significant information.
We're still here.
Yeah.
We may need some water or something like that, but
exactly,
we're still here.
And a big part of it is that knowing what just from what you've done here, could you cobble together an antenna and make it work?
Oh yeah, I think
exactly. So
yeah,
that's ham radio.
Yeah. Well, I've been kind of working with Andy Davis on some MCOM stuff.
Yeah. Okay.
And I live in the Bethel area.
Uh-huh.
There are no hams here, or at least nobody has volunteered to perform the MCOM role of neighborhood ham.
Which is surprising.
Yeah, I know. I was like, so my plan is maybe to go to the Valley Radio Club meeting next month.
It's on the 12th. It's on the 12th, by the way.
Oh, the 12th.
July 12th. It got moved.
See if I can recruit anybody.
We'll be happy to have you.
Okay.
I'm the trustee of the club, so.
Oh, okay, cool.
I wear a lot. I wear a lot of hats.
You're good. Knowledge is power.
July 12th.
Oh, okay. What time? 12th?
July 12th, 7 o'clock, North Kenzie Christian Church up by Costco.
Great, thanks.
Yeah. So let's see. If I were to put up there what I do, ARRL Oregon section manager. Willamette Valley DX Club, VP. University of Oregon technical advisor. W0AXE, that's the South Eugene High School Radio Club tech advisor.
We're busy.
And then there's the VRC trustee. Oh, and I'm also a card sorter. And a volunteer examiner, right? With five different groups. Oh yeah, I mean, you can spend as much time and go into as many things as you want. This is a big, wide, deep hobby. And I'm a cert. Oh, and I'm a contester. Et cetera, et cetera, et cetera. So, I've spent a lifetime, either good or bad, doing ham radio. So, and I still feel like I've barely scratched the surface. So, as I like to say, if you find yourself bored, you're really just not trying very hard.
Yeah, exactly.
You know. All right. What activity involves making as many contacts as possible during a specified period? This is my favorite thing to do on the air, and it's called contesting. The reason that we do this, it gives you opportunities to improve your operating skills, test out your equipment really, really well, test out your strategizing, figure out, truly learn what bands do what at what times of day.
Scott, is that part of, excuse me, Scott,
Yeah.
is that part of field day?
Well, good question, because field day is an operating exercise. There are points, but there are no prizes. So there's nothing to win. So technically it's not a contest, but it behaves like one in a lot of ways. How's that?
Yeah, I just know that the club that's in our area was saying, well, they were so proud of the fact that they contacted so much and so much, and a couple of them contacted the space.
Do they contact the ISS?
Yes.
Oh, that's cool.
So anyway, with doing that, I thought that was part of what you're calling a contest. It's just a matter of pride, then, what you're saying.
Well, it is and it isn't. Field day is not officially a contest.
Okay.
But some people it can be treated as such. I get involved in in a lot of the ones that are specifically called contests, and I'll compete with myself year on year. I'll try to enter a category where I have a chance of actually winning. I went with 5 friends to Vanuatu. Anyone ever been to Vanuatu before? Know where it is? South Pacific. So we went to Vanuatu. It's an island. It's a nation of 83 islands, and we basically went there with the intent of being there for 9 days and setting up equipment and antennas on the beach, and making it kind of like a ham radio vacation. We call it a de-expedition. During that time was a contest called the CQ Worldwide Single Sideband Contest, which is 48 hours long. So there were 4 of us operating that, and we were operating 2 transmitters at once, and on different bands, and kept shifting and sleeping and making sure we got enough sleep and we were awake enough to run the whole thing. And in a period of 48 hours, we made 5,500 contacts in over 100 countries around the world.
Nice.
And so, that's part of, the competition aspect of it. For those of us who are really competitive, I really, really enjoy doing that. So, and then, of course, the rest of the time, we were just there operating. I think we ended up with like 26 or 27,000 contacts in 9 days. And I think it was a total of 150 different countries around the world.
Wow.
Well, I think this year the Eugene field day was supposed to be about like an MCOM event. See how fast you can get the equipment up, and almost like an EOC.
Well, it's a combination of that plus then everything's up. You might as well operate.
Right.
So I actually tallied up the total. It was
Really?
it was just shy of 800 contacts around, and I think 46 states.
Yeah, they had a lot of different antennas.
We had 125 people there over the time.
Nice.
Yeah, I was one of those guys who was up operating until almost 2 a.m. That was me. In fact, I have a feeling that that's what led to me getting this hoarseness.
Think?
I think, yeah. Oh, it was so much fun though. 20 meters was open into the East Coast and Puerto Rico. 20 meters is usually a daytime band. It was still open at 2 a.m.
Wow.
It was nuts. It was the best I'd ever seen it.
We've had some interesting atmospherics lately.
Yeah. I mean, and I literally, the only reason that I stopped, I was having so much fun. The only reason I stopped was because I was literally too tired to keep my eyes open. So the coffee didn't work anymore. Okay, so let's see. Good procedure when contacting another station. In a contest, only the minimum information. If the exchange is, so we asked, what is that 5N9? Okay, so reports that are given are RST, readability, signal, and tone. Well, tone is not given to voice stations. Readability is a scale of 1 to 5. S is signal strength. That's on a scale of 1 to 9. Tone quality is also 1 to 9. So a perfect signal on voice would be 5/9 or 5/9. A perfect signal on Morse code would be 5/9/9. You could also say, if somebody's really strong, you could say 5/9 plus. If somebody is barely on the threshold of being intelligible, you can give them a 2x2, for instance. Very often the S, the signal strength, we can actually pick directly off the S meter on a radio. Okay, next, grid locator. This is another one of those things that I sent everybody. Everybody see this? Everyone see this okay? So this is called the Maidenhead grid square map. The entire Earth is cut up into pieces which are 20 degrees in longitude by 10 degrees in latitude. They start at AA and they end up all the way at, I think, QQ or RRPP. And each one of those is then split into 10 2-degree longitude by 1 degree latitude blocks. These are called grid squares. So everybody can look at this map if you're somewhere in North America and figure out what grid square you're in. The reason we use this is because it's a little more granular than just saying a state. Notice Oregon has like 16 grid squares. Montana has about 24. If you're really nearby, let's say you're talking from Oregon to Idaho, if you're in eastern Oregon and you're talking to someone in Idaho, you might point your antenna almost due north or due east, depending on which way you're going. So it allows us to more accurately point antennas and figure out where we're talking to. So that's a grid locator. To locate sources of interference or jamming, radio direction finding, typically we use a small Yagi antenna or a loop antenna. For a hidden transmitter hunt, we can use a directional antenna. IRLP is the Internet Radio Linking Protocol. It's a form of Voice over Internet Protocol, or VoIP, for sending radio over the internet and vice versa. Echolink is an app which you have on either your phone or your computer, which allows you to register your call sign and use it to get on the air from your computer. So I use this when I'm overseas, for instance, to connect to my local repeater during nets and things. IRLP, and Kent, I'll get you in a sec. Let me just finish this one page. IRLP, you access it over a repeater by using DTMF, which is touch tones, dual tone multi-frequency. And finally, a gateway is a station that connects other stations to the internet. So that's a gateway station. And Kent, are you here, Kent? Come in, Kent.
Yes, I am.
Hello, Kent.
Hi there.
Everybody, this is Kent. Notice his call is KL5T. He's got one of those weird KL calls, which means he's from Alaska.
Good morning. How y'all doing?
Good morning.
Let's see here. So so I don't know. A couple of you have scheduled to test. I'm the chairman of the Anchorage ARC VEC. There are 14 ECs in the country. We are one, and we were the first actually assigned by the FCC back in 1984, and we gave the first exams on behalf of the FCC in 1984. So anyway, we've got a special testing session arranged for you folks. And looks like, Scott, we've got 2 people so far registered.
Wow,
for that.
okay.
We had 3, but somebody rescheduled to later in the month.
Well, it's going to be a
So
small
just
group,
so just 2 people. Is anybody wanting to test at this session?
which is
Is
Sunday at 1 o'clock Pacific.
Yeah, I want to.
Actually,
Sorry.
I'm sorry. This is Teresa. I did schedule to test on Sunday. That was before I started the video Zoom classes with Scott. There is no way I'm going to pass it on Sunday. So I'm going to go back in and schedule mine out a little further in the month too.
Okay, you should have the rescheduling link.
I do.
Okay, good. Yeah, it just helps us keep it all organized if you do that. Otherwise, we have mass chaos at our end.
Yeah, I have the link. I will do that.
Okay.
I would like to test on Sunday, but it looks like you have to have a call sign to
No,
test.
no, no,
Oh,
no.
maybe I clicked. I can go see what I did wrong.
You need to have an FRN.
Oh yeah.
Yeah.
Where do you get an FRN?
Well, okay. Yeah, so you can go to our website and find out how to do it. You can Google how to get your FRN, but when you try to register for the session, it'll ask you if you have an FRN. If not, you'll say no, and then you have the opportunity to go right from the registration site. It gives you a link to go to the FCC site to get your FRN. But yeah, that's probably the hardest part of the process is getting your FRN.
Yes.
And I would just caution all of you, when you deal with the FCC, make sure that you write down and log all of your login information and passwords, please. If you misplace that, then it really makes things a little more complex. Trying to recover that can be a challenge. So, okay. But people do it every day, not to worry. Just follow the instructions. You'll be okay. Uh, Anybody, is it, I mean, how many, are there going to be more folks that want to test on Sunday? Yes, no, looks like yes.
Looks like
Okay.
Seth says he's going to.
I'm planning on registering for the exam on Sunday.
Okay, so just so you,
I saw Sue nodding.
okay, well, we've got a team ready, preparing to administer that exam for you folks. So, Scott can give you the link for that. And just know that when you test there, or on the registration process, there's really 3 steps. Step 1 will be you register on the examination platform, and then you'll receive an email from us, right? As soon as you complete the registration, you should receive an email. You need to look at that email and look down in it because it'll tell you you've got to do 2 other things. And it'll give you a link to a website. It'll say, hey, you got to do these 2 things. So one is you have to pay your $10 examination fee. Okay. And then the other thing is you have to complete your examination agreement form. By doing all 3 of those things, it gets you fully registered and set to go and helps us keep it all organized and nice and tidy and neat. And, it'll all work the way it's supposed to. There are 2, when you do the exam, we use 2 cameras. So that means you simply use, like right now, everybody's in here on a mostly laptop, I guess, as part of this Zoom session.
So
most people they will come in with their second device. They'll come in on the same Zoom session using the same link. Most people will use their cellular telephone. And the reason is we want one camera that's looking right at you, just like you're seeing me right now. That'll be your primary device, and that'll be the computer that you're taking your exam on. The other camera is going to give you a look sort of from the side, so that we can, I'm not giving you a good angle here, but we want to be able to see your computer monitor and your keyboard and desktop in your hands. It's sort of an over the shoulder or from the side look. So just figure out a way to get your device set up so you can get that look. And don't worry, we always figure out a way to get this done, and it works just fine. The key is on the second device, it'll ask you about your sound, your audio settings. for that. And when you come in on that second device, you want to say no, no to sound. Otherwise, it gets painful for all of us. We get some good feedback. Okay. Yeah. And then once you test, what's that, honey? 907. Oh, sorry. A lot of stuff going on here this morning.
You got snow outside.
Snow outside? No
Yeah.
snow outside.
Oh, no snow.
No, it's a beautiful day here. It's in the, that must be in the high 60s right now. It should be in the 70s today.
So the last bit of snow is finally melting.
Oh, it's been gone.
Oh,
Yeah,
okay.
I mean, I'm staring out of the field of flowers out here, out the window in the lake.
The 2 weeks, the 2 weeks of Alaskan summer, huh?
Something like that. Yeah.
So did Anchorage break the record for snowfall? It was close. I know that.
Yeah, I know. We got a lot of snow this year. It was, yeah, a lot of snow.
I was there in 2012, 13 when it was 135 inches.
Yeah, well, it just kept coming this year. You know, we didn't lose a lot of it during the winter, so yeah, it piled up pretty good. Yeah. So anyway, when you finish your exam, we will submit that to the FCC. It'll be the weekend, so they won't process until Monday. I guess it won't be a holiday. They'll process. You should expect an email from the FCC after we make the submission that will tell you to go pay them your $35 for your license. And when you do that, you're going to want to do it on your do it on the computer. Avoid using your cell phone.
Yeah, it's really hard on the cell phone.
They have supposedly fixed their website so that works better, but just to avoid problems, just use a computer to make that payment to the FCC. You know, and then usually after you pay, your call sign will be issued typically within about 24 hours. Okay.
And don't try to register for an FRN using your phone. We had somebody do that recently.
Yeah.
You can do it,
Yeah.
but don't do it.
Yeah, just when you're dealing with the FCC, use a real computer because it'll trust us. Ask us how we know.
Mm-hmm.
Yeah.
I can vouch for that. It was a night.
Yeah. And these, yeah, it is a little confusing. Just kind of hang in there, follow the instructions. The ARRL has some good instructions on it, but the FCC website actually has some instructions that are okay if you can find them. But you'll be okay. Everybody that we've had ever had to do this, they've all successfully gotten their FRN, so not to worry. What else? What else you want to know about? Nothing. You learning stuff from Scott?
I hope so.
Yeah.
I hope
and
so.
yes,
Can you get a personal identification number or something close to it at the, like if you got favorite numbers at the end of your call letters?
Well, okay.
We'll get to vanity calls. We haven't done that yet.
That's what I'm talking about. Yeah.
Yeah. Well, yeah. Like Scott said, that's vanity, and that's a different process. You'll do that after you get your license. So you're going to have to. You will be issued a license in sequence based on your location by the FCC. Once you have that in hand, then you can go forth and see about getting a vanity call sign if you'd like.
Just numbers that I know I can remember easy.
Well, don't worry. If you're active in this, you won't have any problems remembering your numbers. Just like it's ingrained in every ham what the national calling frequencies are on 2 meters and 440, right? National calling frequency on two meters is test question.
Come on, everybody.
Come on.
146.
146.
Dot.
552.
There
52.
you go.
Yep.
And I don't know if they ask the UHF national calling frequency, but
They don't.
446.0. So anyway, yeah, we end up remembering weird stuff. So that's one of them. Okay, what else? Nothing? All right. Well, we look forward to testing y'all.
I got a question real quick.
I just looked on the FCC website. Where would I register for a test in my area?
In person? Okay, well, hold. The FCC doesn't do tests.
Nope.
Okay. That's tests are administered by DEC. So you can go to the ARRL website. Just simply Google ARRL or find a test location, and they have a website that you can go to, and you can put in your zip code or your city and state or whatever, and you can find out where in-person exam sessions are being held and when.
That would be in person. If I want to do it over the internet, is there a location I can find out how to get it done on the internet?
Yeah, you just go to our website.
Whose website?
KL7AA.org.
Okay, gotcha.
KL7AA.org, license testing, and then you'll hover over that and click on remote testing.
Gotcha.
And then you can see, we test, so just so you know, we test every day, twice a day, Monday through Saturday. Okay. So, but for you guys, we're doing, if you're ready to test, we're doing a special exam session for you folks. If we have a pile of you, we won't be able to do you all at once. We'll take a group of 3 or 4. We'll open a testing window, and we'll ask that you be available for about a 2-hour period. And then we'll call you when it's time for you to join the session, because we can do about 3 or 4 at a time. So we'll get the first group going, and then we'll start bringing people in one at a time as other examinees get done. So
okay.
Please don't join the Zoom link, because Scott's going to give you the Zoom link, or you're going to receive, if you register, you're going to receive the Zoom link for this. Please don't join until we call you, because we're trying to manage. We're herding cats, man.
Everybody's
right.
anxious. But,
yeah, we're herding cats. Everybody wants to go, but just hang in there. We won't forget about you. And if you do need to test early, let us know that too. Or if you need to test at kind of a certain time because you got stuff going on, we'll make that all work. It's all good. No problem. All right. And don't worry. Remember, when you come to test, you're going to be with friends. Okay. You're going to be all of the volunteer examiners. We've all been there. And our objective is to get you your license. We want you to succeed. So we're cheering you on. So just remember that, okay? Any other questions?
This is Steph. I have a question again. It sounds like you're going to call us on Sunday. Yep. So the plan should be on Sunday morning to not do anything until we hear from you.
Well, I think it's 1 o'clock in the afternoon.
I just signed up. It looks like it's listed as 11 o'clock.
It could be 11. Let me see. It's a special session. Could be.
It's at, oh, yeah, I've got a couple more people registered here. Let's see. Yeah, it's Sunday at 11 o'clock Pacific time.
Oh, good. I'm glad I mentioned. I'm glad you mentioned it.
Make the adjustments for yourselves. No, and I don't know how to present, but it's listed on the website as 11 o'clock Pacific time. But I think when
KD, I think put it in at 1 p.m., but we can start at 11. That's fine. I don't know what time he has people coming.
So the window opens at 11.
It appears that way.
Yeah, it opens at, sessions scheduled from, we've got it listed from 11 to, he's got a 4-hour window, 11 to 3, but it won't last that long.
No.
We'll get y'all done way before that.
Way before.
Yeah. So it looks like we've got 4 people at least partially registered right now. No problem. That's easy. But we'd like to do 30. We can. 1, 2, 3, 4. Yeah. Let's go.
All right.
And
cool.
and if you're and look, if you, so I do encourage you. We encourage you to take practice exams beforehand.
Out the wazoo.
Yeah, out the wazoo. And you can do that on hamstudy.org. There's a lot of sites you can take it on, but take practice exams and if you're scoring regularly above 80%, likely you're going to have no problems passing the exam. And if you do, on a data exam, when you take your exam, if you're close, like within 1, 2, or 3, and you say, yeah, I've been taking practice exams and I'm usually passing, we're going to let you try again. Okay. So we want you to pass. All right. What else?
Let's go finish this off, shall we?
All right. Good luck, everybody.
Thank you.
Good
Thanks,
test, you
Kat.
guys.
Thank
See you
you.
later.
Thank you.
Bye.
Thanks
Thank
a
you.
lot.
Thank
Bye,
you.
everybody.
All right, here we go. Woohoo! We're into my least favorite section, but the one that you can't get around, which is rules and regs. There's no way around this. And there's nothing else to do other than memorize. Everybody see those rules and regs?
God, can I interrupt you a moment before I forget?
Yes. I sent you the stuff.
You did?
I just did
You
a few minutes
rock. I
ago.
haven't looked. I've been here.
I sent them as individual attachments.
Yay!
So,
Thank you so very much. I appreciate it.
okay. Part 97 of the Code of Federal Regulations is all the rules. There are the rules in the Code of Federal Regulations. They're actually part of the United States law. The FCC is responsible for enforcing the rules. That's the Federal Communications Commission. Okay, notice it says 97.1, 97.3A9. That's actually the spot in the FCC rules where this stuff shows up. So we could torture everybody by pulling up a copy of the FCC rules. Just for the heck of it, let me see if I have that here. I did not. Okay, so we're going to have to go get it on the internet. So FCC Part 97. Part 97. Here we go. Part 97. Here is Part 97. Whoop. Notice just your standard old little rule book. Rules, rules, rules. Notice how many pages of rules there are. Basically, this governs everything ham radio. Part 97 is ham radio. The first part of this is actually really significant, though. Right here where it says basis and purpose. This explains why we are allowed to exist. Ham radio has existed for over 120 years. It was originally the experimenters that wasn't codified. It was all the people who were experimenting with radio in the early days. Then the military discovered, oh, you know what? We can actually use these really low bands below 200 meters for military purposes, and we'll let all those hams, the amateurs, use the higher frequencies because they're pretty worthless. Well, it turns out nobody had discovered ionospheric propagation yet, which it turns out is a lot of fun, as well as all those communications with satellites. And because, in 1905, 1910, we didn't really have satellites to speak of. So there was no reason to even think that we could talk to satellites up in space. So we ended up with these garbage frequencies, which it turns out were the really cool ones. And then it ended up spreading worldwide, and we have hams in virtually every country except North Korea and possibly Turkmenistan. Although technically, if there were hams there, they could operate and we could talk to them. So it is important to note the rules, the reasons why we exist. Public, voluntary, non-commercial service. This is very important. Non-commercial communication service, which means we don't make money. The word pecuniary comes into play, which means earning money. We are not allowed to earn money for doing what we do. We don't pay anything for the most part, and we don't earn any money as part of what we do. We're volunteers. Advancement of the radio art. Advancing skills in the communication and technical phases. So that's why, for instance, single sideband was created for the ham radio community in 1956. It was used throughout industry since then, for all the military services and aircraft, etc., etc. Expansion of the existing reservoir of trained operators, technicians, and electronics experts, We are one of the STEMmiest of STEM hobbies that there is. And continuation and extension of the unique ability to enhance international goodwill. I particularly like this one. When I was applying for my first job, my first real job, back in 1990, I had to take I had an interview for a security clearance, and they said, do you have any communications with people who are in unfriendly countries? I'm like, well, what is unfriendly countries? They said East Germany, Romania, Russia, Soviet Union. I was like, Poland. I said, yes, 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 yes. Like, well, in what way? They said, well, I'm a ham and I talk to them all the time. To which they said literally, oh, don't worry about it. You're good. Because part of being a ham radio operator is as a goodwill ambassador. So that was really cool to me. I have lots of contacts and QSL cards from behind the Iron Curtain when that was a thing. Okay, so the definition of a beacon. A beacon is beep, 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 sends out information. It's a one-way transmission for observing propagation or related experimental activities. A space station is anything 50 kilometers above the Earth. Purpose of observing. Oh, that's weird. There we go. 50 kilometers above the Earth. When are you allowed to commit willful interference? The answer is never, even if they're really annoying. You have a tuning knob. You can feel free to spin the knob and go somewhere else. There is something called a volunteer frequency coordinator. This is basically somebody who administers the band plan. This is typically true on VHF and UHF frequencies. Notice auxiliary and repeater stations. Those are mostly VHF and UHF, although not exclusively. A frequency coordinator is picked by local hams in that area. So in Oregon, we have the Oregon Region Relay Council. Every section, every state has its own version of that basically assigns frequencies to keep the peace. All right, so now we have to look at this band plan, and we have to look at the 6-meter band, and there's no other way to do this other than memorization. So if we see the 6-meter band, we look on the 6-meter band chart and see that it covers from 50 to 54 megahertz. That's just memorization. Okay, so which one of these is in the band? We know that it's 52.525. 146.52. We look at this, we see the 2-meter band is 144 to 148. So it's the 2-meter band. On what band does a technician class operator have phone privileges? Well, we have technician, novice technician voice. Notice this blue hatch down here at the
cut out for anybody else.
Very much so.
What?
Yes. Yeah, go.
Scott, we lost you.
Up. Okay.
For just a minute, you're back now.
Did it come back?
Yeah, he's back.
Yeah.
Okay.
We can hear you now.
Yeah, that's weird. Okay. I guess I had a little
Just
glitch
2
here.
seconds.
Yeah, okay. Okay. So on the 10-meter band, a technician class operator has phone privileges because the band chart right there says so. Same thing. Asking the same question a different way. Where can single sideband phone be used above 50 megahertz? Well, we look at this. We see SSB is this greenish olive area, and we see that every band above 50 megahertz has at least one little section for that, and that's known as weak signal. Which of the following band segments are limited to CW only? Well, okay, CW is red. Can look at these and see, oh, there's a red one, and there's a red one, and there's a red one. And we look over here and we see the choices that select those frequencies. There we go. So again, this is all just, rote memorization and knowing the band plans. If you do intend to take the technician, the general class exam, really the only significant change as far as memorization goes is knowing all this stuff below 10 meters wavelength frequencies. You have to know what the band edges and power limits are. That's really the significant part of the rules that changes. 219 to 220. You notice at 219 to 220, oh my God, it's not even on this. So a long time ago, it's probably 20, 25 years, this band actually, the 1.25 meter band, which is not very busy, went from 220 to 222. The reason it's not very busy is because there's not a lot of commercial gear made for it, because in Japan, where a lot of equipment comes from, they don't have this band at all, which means that they don't make a lot of equipment, which means that handheld radios typically don't include that band. So there's not a lot of activity. Well, it used to go from 220 to 222, and a company that drives brown trucks came along and said, we'd like to use 220 to 222 as part of our parcel delivery system. And in exchange, we will give up 219 to 220. Kind of a weird exchange, right? So this band, we have 222 to 225, also includes this little outlier thing from 219 to 220, and it's for fixed digital message forwarding systems only. In other words, data. That's all we can use it for. I don't know anybody who uses it, but it's on the test, so it could be asked. Why do you not set your transmit frequency to the exact edge of an amateur band or subband? All right, so for this, I'm going to ask you guys a very important question, and this is to see how well you've learned what things look like. So here's the frequency spectrum. Here's our center frequency. All right, what does an AM signal look like compared to that center frequency?
Big peak.
We have stuff below it and stuff above it. Okay, now what we're going to do is look at our band, and see that 2 meters is 144 to 148. Does the FCC tell us what frequencies we can specifically use in that band? This is another place where ham radio is unique compared to like FRS, GMRS, or any other band for that matter. Those are channelized. Does the FCC have any say as to where we are within those limits?
No, it's the band.
No, it's a big old sandbox. We could be pretty much anywhere, which means if we want, we could put that signal we just drew right there. Legal or not legal?
Legal.
Legal. How about right here?
Anywhere.
How about right here? How about right here?
Well, then you're bleeding out.
Then you are over the band edge. That's right. So basically, that's why we never tune right to the edge, because that's another part of being licensed. Another part of being licensed is understanding that with that big sandbox comes a lot of responsibility. The sandbox is huge. We have to know how to keep our toys completely within the sandbox, which means we have to know that we can never do that. We can go here if we know that our signal goes only to the edge. Right? With great power comes great responsibility. Okay.
I have a quick question.
Yes.
It would be an example of like being right on the edge, or like what's.
Oh, it happens. It happens all the time.
Yeah.
You want to see? Okay, so those of us who are contesters, we're always looking for space, because during a contest, the band can get very crowded. The phone band, phone is voice, goes from 14,150 to 14,350. And we are using upper sideband. Upper sideband is a signal that looks like that on this spectrum. This band, you will see signals like this all up and down the band. If you want a clear frequency, good luck, right? You might find one, but good luck. So every so often you'll hear somebody calling CQ on 14.349 because that's the open frequency they could find. Can you answer them, yes or no?
You shouldn't.
Because your signal is how wide?
3 kilohertz.
And you know that if you tune to 14.349, your signal is going to go all the way up to 352, which is outside the band. This happens all the time. And it results in notices of, a notice of violation, not from the FCC, but from an official observer, or I'll even write somebody. I'll send them an email and say, hey, you were out of band, just so you know. It might have been clear, but you're not allowed to be there. And I won't answer them, so. And most other people won't answer them either. Again, we're largely self-policing. It's better to get a note from one of your fellow hams than from the Federal Communications Commission. So, okay. Amateur radio operators sometimes share bands with other users from other services. How are we limited in places that we are secondary? If we're primary, that means we are primary. We're supposed to be there first. If we're secondary, that means that somebody else is primary, and we have to defer to them. So, for instance, if we look at our frequency chart, we will see that this giant wide open space of 420 to 450, actually, this is a secondary allocation. We are secondary to the military. So if we hear military stations up here operating there, we actually have to move. Not them. Except for some specific restrictions, above 30 megahertz, you are allowed to run 1,500 watts. Again, another good reason why we're in class. You can cause a lot of harm running 1,500 watts of RF. On the high frequency bands, you're allowed 200 watts of output power, which is more than most transceivers will even put out. Most normal transceivers are 100 watts max. License classes. Okay, things you can get. Technician, general, amateur extra. No, I don't know why it's called amateur extra. It's amateur anyway, right? Why isn't it called amateur technician and amateur general? A license is good for 10 years. You can operate as soon as your license appears in the database. Now, notice this operator/station license. There's actually 2 separate licenses that go with each license. There's an operator license and a station license. The operator licenses you to operate, and the station basically identifies the station with a call sign. So, for instance, if I were to have a club station, and I'm a member and I'm a trustee of a club, and we have a call sign of W7PXL, which we do, and it's a club call that has a station license, but no operator license. In other words, this station, which is at the Eugene Science Center, cannot be operated by somebody who doesn't have a license, even though the club equipment is there and has a call sign associated with it. There's an operator license and a station license, and they are 2 separate things. Now, if you get a call sign, it includes an operator license and a station license. So it's both. But a club call sign, a club station, will only have a station license. The person who walks in becomes the control operator of the station. And believe it or not, the station carries the call sign, the license privileges of the control operator. So if this person has a technician class license and is the control operator of the station can operate with technician class privileges. If somebody walks in with an extra class license, then the station can operate with extra class privileges. If you have 2 people who walk in, you have an extra and a technician, those 2 people walk into the room and are the control. One is the control operator. Who would be the most likely control operator?
The extra.
The extra. Okay, so the station is operating with the extra class band. and the extra walks out of the room to go to the bathroom, what has to happen?
Then it drops down to a technician.
It drops down to a technician. Exactly. Okay. How many station and operator primary station license grants can be held by one person? That would be one. The proof of being in the database is being in the database. If the FCC database says that you're valid and active, then you're valid and active. You don't even have to have something on a piece of paper. They don't even mail you anything when you get your license anymore. Okay, a vanity call sign can be selected by any licensed amateur in the United States. Okay, every call sign in the United States begins with one of 4 letters. It begins with, we have all the W's, and we have all the K's, and we have all the N's, and we have A's from AA through AL. Every so often, somebody will, let's say you have a technician class license. You have a 2x3 call sign. KA7OPK. That is valid for anybody. It's a 2x3. W7OPK. That's a 1x3. That is valid for any license class. But then you could have WA7OM. That's a 2x2. That's an extra class license only. N7OM is a 1x2. That means basically every call sign has one number in it and a certain number of letters. That's extra class only. NM70, that would be a 2x1. That's extra class only. So here's the dividing line. Every so often, somebody who has a technician class license will see a call sign that they like. That's an extra class license. And submit it to the FCC, at which time somebody at the FCC will say, nope, can't do that, and just reject it. The other thing that happens is that every so often somebody doesn't understand the call sign allocations around the world and will say, my name is Billy, and they'll put in for B1LLY. Somebody at the FCC will get a good laugh and then reject it. And why is that? Because that call sign's owned by China. It's like, yeah, we can't assign that. Sorry. So this happens more frequently than I care to think about. So it is important to understand that the United States has access to those call signs only. If you go to other countries, for instance, SP, that's Poland. DL is Germany. G is England. VK is Australia. V8, that'd be Brunei. And there are many, like J8 is Dominica, and Victor 5, that's Namibia. So all of these that you might be interested in getting, we don't have access to in the first place. So we have W, K, N, and AA through AL. So when you go to choose a vanity call sign, keep that in mind. So
Yes,
that's
Scott?
Yeah.
Quick question. I apologize if it's already been covered and I just can't recall. Right now I have a GMRS license. Now I passed tech. Will I have 2 call signs?
It's totally different. They have nothing to do with each other than the fact that you already have an FRN.
Okay. So essentially I'll have 2.
Yeah, they have absolutely nothing to do with each other.
Gotcha. Okay.
Yep. The grace period for renewal is 2 years. After 2 years, you have to re-examine. Go ahead. Okay. During the grace period, if you are listed as inactive, expired, you have to wait until if you sent in an application during the grace period, you have to wait until it shows up in the database. A club has to have at least 4 members. That's the definition of a club. It also has to have, in theory, it has to have a constitution. It has 4 officers, so it's a club. If the FCC can't reach you by email, this is really important. If the FCC can't reach you by email, they can pull your license if they see fit to do so. In other words, keep your information current. When filling out your license, you have to put an address. You can even use a P.O. box. A lot of people do that. Which of the following is a valid place to transmit from? If you're on a boat in international waters and it's in a United States registered boat, it is part of the United States. Your call sign is valid from there. You still, if it's a larger boat and there's a captain, you need to ask permission, but your license is at least valid. As far as indecent or obscene language, you are prohibited from doing that. Basically, the rule of thumb is that if you wouldn't say it to an 8-year-old or younger, don't say it on the air, because you never know who's listening. When are you allowed to transmit music? Only one time. This came about when when NASA Goddard and Johnson Space Flight Centers and probably JPL used to rebroadcast space shuttle transmissions over their repeaters. And occasionally they would send wake-up music. NASA would send wake-up music to the astronauts. That would come out over the air. And the wake-up music is technically, we're not allowed to we're not allowed to transmit music. You have music stations to do that. So this is the only time when it's incidental to manned spacecraft communications that we're allowed to transmit any music. You would think also, considering that we're not allowed to obscure any messages, that we would never be allowed to obscure messages. But that is actually not true. Let's say that we have a space station. We are allowed to launch and control our own satellites. We have many amateur satellites up there. We can also have remote control craft, such as a first-person vehicle drone, or an RC plane, RC car, RC boat. We don't want somebody crashing it on our behalf. So what we do is we are actually allowed to encrypt those signals. Who are we allowed to exchange communications with? The answer is anyone, unless their government says tells the ITU, which is a part of the United Nations, you're not allowed to talk to our people because we don't like you. This rarely happens, believe it or not, between the United States and North Korea. We're actually allowed to talk with them. If anybody were ever licensed in North Korea, we could actually talk with them. The only instance I know was that there was a group in, I think it was Yemen. They were on one of the islands, and they were specifically told you can hear even if you hear Israeli stations, you're not allowed to talk with them. Sorry, because apparently they're still at war with Israel. I guess this was a few years ago. So unless they tell the ITU they're not allowed to, then it's okay. When can you receive money for operating a station? Well, remember I said that you're not allowed to receive money for operating ham radio? There's an exception to every rule. If you're a teacher and you're using ham radio as part of your instruction, you can still collect your salary. So if you're operating, you're a teacher, that's okay to still get paid. When can you use your stations to notify other amateurs of the availability of equipment for sale or trade? So basically, if you're not running a business, some people say the rule of thumb is, a couple times a week. That's probably pretty fair. Now, you could say, would this be valid? Hey, I have a car that's completely decked out with radio equipment for $4,000 for sale. Would that be considered okay? What do you think? I think it would be okay. Now, if you'd say, I have a riding lawnmower for sale for $4,000, maybe not then, right? Or if I've got a 2-meter handheld radio for $25, that would be okay. If you'd say, you know what, I have a couch that would really be good for a ham radio station, and I want to sell it for $50, maybe a little iffy. And especially if you, personally, I would be okay with it. But if you did it on a regular basis, then probably not okay. Broadcasting. We don't broadcast. Broadcasting is done by commercial entities. We transmit for reception by That is transmitted to the general public. We don't do that. Our interest group is other ham radio operators. So if it's being transmitted one way, if it's us, it's one-way transmission. If it's commercial, it's broadcasting. So we don't broadcast, so you can forget ever using that word. We don't broadcast.
So a question about that.
Uh-huh.
So are there just certain frequencies that are allocated to broadcasting, or
if it's a commercial station,
it's a okay,
or if it's like NOAA weather radio station 162.400, they broadcast because it's intended for the general public. If we're sending out like beacons or something, it's a one-way transmission because the general public has no real interest in it. So, yeah, it's really a question of semantics at that point.
So it's kind of defined by the content of the information
and who it would be usable for, who would find it useful. Okay. Under which of the following circumstances are one-way transmissions prohibited? That would be broadcasting. So we can send out Morse code practice. We can send out telemetry. However, we are also able to support broadcasting, even if we're not broadcasting ourselves. If there's no other means necessary, when it's about immediate safety of human life or protection of property, like there's a dam that's about to burst, we have to get this information to the local news crew. That would be immediate safety of human life and protection of property. So what are we allowed to talk about? Right there in the FCC rules, 97.117. Right, there it is. If we were to look at 97.117, I'm going to pull it up right here. And you know, when worst comes to worst, you check with the documentation. Thank God you can do a search. International communications. Notice what it says. Transmissions to a different country, where permitted, shall be limited to communications incidental to the purposes of the amateur service and remarks of a personal character. So we think back, the purposes of the amateur service are all the way at the top. So if it's any of these things, right, that's our purpose, or remarks of a personal character. So what would be included in remarks of a personal character? What do you think?
Yourself?
Yeah. Oh, my back. I have a doctor's appointment coming up next week. I used to laugh when I heard all the people groaning about that. But those are remarks of a personal character, are they not? People talking about all their medical afflictions. You know, like I said, I was 15 when I got my license. It was just crack me up that people would be on the air complaining about how lousy they felt and having a doctor's appointment they have to go to, and I have a colonoscopy next week. Well, now now I kind of get it. So you get to a certain age where that's, like the biggest thing that's happening in your life. So control operator and control types. When can you operate it without a control operator? That would be like a club station. If there's no control operator, the answer is never. Now, interestingly, automatic control is still considered having a control operator. I am the control operator of our club repeater. It is operating on a mountaintop even though I'm not there. I'm not actively listening at this time. It's operating automatically. Am I responsible if something goes wrong? Yeah, maybe. If somebody tells me, I would probably jump into action and talk to somebody and have them drive up there and see what's going on. Let's see. Who does the FCC presume to be the control operator of a station? That would be the station licensee. So, if I have a station and somebody else, I've given permission to use it, it assumes that unless that has been documented, I'm responsible for the proper operation. The station licensee designates the control operator. So my friend comes over, I said, go ahead and use my station. That's the control operator. I'm still the owner of the station. When the control operator is not the station licensee, who is responsible? Notice who's responsible now. I'm still the owner of the equipment, and the control operator is as responsible as well. So basically, whoever's involved, whoever has their name on it, they're involved in the station, and if something goes wrong, they're supposed to fix it. What if a repeater inadvertently retransmits communications that violate the FCC rules? Somebody gets on your repeater and they think they're really funny and they start playing and they open the microphone and start playing music off the radio. Who's responsible for that? Well, it was automatically repeated, which means I can't really be held responsible as the control operator. Ultimately, it comes down to whoever was the originating station. That could be licensed or unlicensed. And they're the ones who are subjected to the FCC fine. Transmitting frequency privileges are controlled by, as we said, the operator class held by the control operator. Under what circumstances? Normal circumstances. Can a technician class licensee be the control operator operating in an extra class band segment? This is the example of me being the extra class operator and walking off to go use the bathroom. Leaving a tech can't be the control operator right there. So a satellite anybody can uplink to the satellite if they have privileges to transmit on the uplink. Even if the satellite retransmits them somewhere else where they don't appear to have privileges. They didn't move the signal. The satellite moved the signal. The control point is where the control operator function is performed. That could be the push to talk button. If it's remote control, a lot of people now operate remote control. If I am on a computer and it is connected over the internet to my station at home, that is the control point, me at the computer. And if you are doing that, the control operator must be present. The controller operator is always supposed to be there. And the control operator indirectly manipulates the controls over the internet. Automatic control is repeater operation. Okay, station identification, repeaters, and third-party communications. So we have this thing called third-party communications. The third party is the station who doesn't have a license, who you are allowing to use your privileges. You have to be there. You're responsible for everything that comes out of their mouth and goes over the air. I have once in my life, because I operate from our local museum, been the control operator for somebody and I actually had to slap the microphone out of his hand. It's like, I don't know where you were going with that, but I couldn't risk it. Sorry. You're required to transmit your call sign at least every 10 minutes and at the end. You don't have to use your call sign when transmitting signals to a remote control craft, so an RC airplane. You're also limited to 1 watt when you're doing that. When you're in a phone subband, you have to identify in the United States in the English language. Your entire conversation could be in Swahili, it could be in Swedish, it could be in Spanish, but your identification, November 7, Juliet, India. And then you can go back to speaking whatever language you want. How do you identify your station? Using Morse code or using phone. Phone is otherwise known as voice. N7JI. You can also have it go in the background, dot it, dot dot it, dot 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 it, which is what we do on repeater stations. We have repeaters using Morse code so they allow somebody to talk and not be obscured by the Morse code. The phonetic alphabet is strongly encouraged. It is a good idea to know your phonetics because phonetics get through when other things don't. For instance, the letters P, T, C, B, E in noise can all sound the same, but Papa, Tango, Charlie, Echo, and Bravo all sound different. So that's why we use phonetics. Tactical call signs. Let's say that you are operating at a race and your race headquarters are Station 1 or Station 2 or Station 6 or Aid Station 7. You can use those call signs, but you're still a ham licensee. You have to give your call sign, your actual call sign, every 10 minutes and at the end. So the rules still apply. You can also do self-assigned indicators. A self-assigned indicator is something that goes after your call sign that doesn't change your call sign at all. It just says that I am operating low power or I'm operating in a different zone of the United States. So for instance, KL7CC, stroke or slash or slant W3 would mean that you're operating in the Mid-Atlantic region. Avoids confusion. It's not required to do that, but some people might find it confusing if you didn't.
Scott, I got a question real quick.
Okay.
You would, in one of the questions just previous, you have to, do your call sign every 10 minutes and at the end of your communications.
Mm-hmm.
But earlier when you were talking to, I believe it was Toto, you guys were using your call signs at the beginning also. Is that just kind of a format or is that a requirement?
You are not required to. However, if there's one thing that hams like doing, it's use their call sign. I mean, you earned it, right? But there are times when, you'll just break into a conversation and they'll know who you are. And you're not required to do so. The requirement is you have to give it at least once every 10 minutes and at the end.
Okay.
But again, especially if it's somebody you don't know, then you're going to throw out your call sign.
I actually had the same question, so thank you.
Yeah. Yeah, it's kind of a weird bug in the rules. I mean, who doesn't give their call sign at the beginning? But it's not required. Like I'll sometimes I'll break into a conversation and they know who I am and I certainly know who they are. And after 3 minutes, I'll give my call sign. Because it seemed like it was extraneous at the time. All right, third-party communications. So, if it was, let's say, Toto on one end and me on this end, and we're having a conversation, and Toto says, hey, I want to get my mom on to talk to you. I say, okay, that's fine. And you know what? Oh, and my mom wants to talk to your wife. So I would get my wife. And then you'd basically have two non-licensed third parties talking to each other. In the United States and Canada, that's fine. Between the U.S. and any other country with which we have a third-party agreement, it's fine. With some countries, we don't have a third-party agreement, like Japan, oddly enough. A lot of European countries we don't have a third-party agreement with. The reason being that for many years, the government ran the telecom company, and the government also gave out ham licenses. So if the government were to permit hams to allow non-licensed people to circumvent long-distance phone charges, they would have been taking money away from themselves. So they didn't allow that. There's no reason for that to exist now, but they've just never gone back and fixed it. And finally, if the FCC knocks on your door, you have to open the door. This is very rare. You have to have done something pretty bad for this to happen. Once in a while, it does. Like, hey, your signal was heard interfering with air traffic control. Cease and desist now while we figure this out. That happens once in a while, but it's pretty uncommon. And guess what? It's 12:30, and we did the whole thing. So now it's time for questions, and now it's time for clarifications, and now it's time to discuss how you feel about going and taking an exam, and what works for you and what doesn't work for you, and doing some of the mechanics of this whole thing.
I looked at my emails, and I did get the PDFs that you sent. There are more than I was expecting. And thank you so very much. And I think that they will help me along in my studies. I have been studying, not as much as I should have been, on the practice exams. And as you're going through these parts and the 97 rules, I actually couldn't believe it, but I remember almost every single one of those from the practice test. So I'm pretty shocked by that. So I might wait a day or two before I reschedule.
Yeah. Well, and the thing is, seriously, go through and do it section by section using whatever app it is, because it's just like, okay, I actually, I don't know if I mentioned, but I went through just to see if I could do it. I was recently in Canada, and I was encouraged by one of my Canadian friends to take the Canadian license exam.
Oh, cool.
And in the United States, okay, let's see how good you guys are at remembering this. How many questions is the technician exam in the United States?
35.
35. And you need to get how many?
26.
Okay. And the general exam is the same thing. And the extra exam is 37 out of 50.
Oh.
All right. So when I went to Canada, I started studying back in like October. And I just did this last month. So I gave myself some time to do it. I found some study guides. They're online practice exams, not section by section, but on the Canadian ISED website, which is their version of the FCC, basically, or Department of Commerce. And they have 3 levels of exam. So this is the technician, the general, and the extra in the United States. In Canada, they have basic with honors, and advanced. This basic and basic with honors is one exam. It's 100 questions. If you get 70, you score basic. That's the equivalent of a technician exam. If you score 80, you get the equivalent of a general license. The advanced exam, which is the equivalent of extra, is 50 questions, and you need 35. So it's somewhat similar, but look at the length of that basic exam. And I got to be honest.
Yes.
I was really nervous studying for that. I did pass, by the way. So.
Well, congratulations.
Yes. So I actually hold the call VA7NJI. I have N7JI in the United States and VA7NJI in Canada. But it was interesting because I hadn't taken a radio licensing exam in 37 years.
But he teaches the class.
And it was a little daunting. So but it's the same kind of thing where their question pool was 1,000 questions. Of which you'd be asked 100. You got to take a lot of practice exams to know that whole question pool.
Oh my goodness.
I did. I mean, I took 6 months to study for it. But I ended up getting a 97 on this one and a 98 on this one. So it ended up working out, but it's the same thing. You got to prepare. There's no way to get around having to prepare for something like that. And I was just reminded of that when I took that. So same thing here. The only way to really be comfortable with it is by studying enough and practicing enough. And fortunately, there's no real time limit. There's no time limit on the exam. There's no time limit on how much time you have to study, other than the one that you impose on yourself. So. But
one other thing, when you were going through all the electrical stuff, all I knew about any of that was what I had memorized from the practice test. And you were explaining it, and I actually had gone and downloaded a book on electronics for dummies or something like that. And I'm like, that is absolutely my weakest point, and I know that. But I'm your videos are going to be more helpful to me than going back through that book, I believe. So I'm definitely going to do that again, and I'm contemplating going on and doing the general at the same time I do my tech. But I want that extra time, and that's another reason that I want that extra time, because now that's a bit of a confidence booster. It's still over my head, but I have more grasp on it than I did.
Yeah, and you know the differences between the general exam and the technician exam is you'll add some vacuum tube stuff, but it's fairly minor. The math, there's a few more different mathematical topics. You really don't get too much math until you get to the extra class exam.
That was going to be a while.
Yeah. Well, but you know, I think back to when I did these exams, and I was 17, and I did not know the theory behind it. I basically, you know, I'm not embarrassed to say I did each one by memorization. And you know, like now I can go through and I know exactly, you know, how to calculate root mean square. I know how to calculate average power and all that stuff. But back then I just had to go through it and memorize it.
Yeah.
And
I have been resistant to that approach because it's not how I normally do things.
Yeah. Well, but and what I've really found out is that it's best to do both.
Yes.
You memorize it, but then if you forget how something came about, you can always rederive it. Which is why I think, you know, having even something as simple as this, right? The EIR circle.
Yes. That was great deal, by the way.
The reason being that I still have to go back and think Ohm's law. E equals I times R. I want to solve for R, so I divide both sides by I. So R is equal to E divided by I. I still have to go through that on paper to make sure I don't screw it up.
Yeah.
I've been doing this my whole life, and I still have to go through and make sure I don't screw it up. So that's a way to make sure I don't screw it up.
I've had people telling me for a year, oh, my 12-year-old granddaughter just memorized the test school questions. She passed it.
Well, my 12-year-old son did. He did.
So
That's exactly how he did it.
Them. It's just that I wanted to understand what I was doing. I mean, I'm medical. That's how my brain works.
Yeah.
But and again, I'm going to have a combined approach for this one.
Yeah.
Yeah.
Any other questions or thoughts, everybody? It's a good time to ask questions.
I just wanted to briefly ask, when referring to all of the network and what space you're supposed to be using, and you know the band plan and stuff like that during the test, we just have to memorize what it is we can't use a cheat sheet.
There's no cheat sheet.
All right, thank you.
But you could say but you're allowed to do stuff like this. So let's say that someone says, what frequencies are in the 6-meter band? How long should an antenna be? Okay, so let's say they want to pick an antenna for 52 megahertz. How long should the antenna be? Well, okay. What's the first thing we do? Right? You always start somewhere.
Hello.
Right? So we don't know this one. 300 divided by 52 is approximately 6 meters. And we want a quarter wave, let's say. So a quarter of that is 1.5 meters. And we take 95% of it because it's a little bit too long. Is 1.4 meters. And then 39 inches per meter and then you can figure out that it's about 54 inches long. So, I mean, and this, but this kind of stuff is the exact same kind of stuff that you'll just scribble down. This will become kind of like second nature. If you're thinking, how long does this antenna have to be? Could I put that on a car? Actually, could you? 54-inch long antenna? Could you put it on a mag mount on the roof of a car? I've done that. I mean, when you're driving fast, it kind of blows like that. It sort of bends. If you go to McDonald's and you go through the drive-through, it does like this. Where they say max 8 feet. Boing is the sound. I had on my old car, I had, because I lived in a homeowners association community, I couldn't put anything on the house. So I had, here's my car. So the base of the antenna, that was 3 feet. And then I had a 102 inch, which is 8 foot 6 inches on top of that. That was on the back of my car. And it worked great. The only problem is, if you see a sign that says clearance 10 feet, you're not going to make it. Or you're going under a bridge or an overpass, and it looks like this.
Yes.
Right? Where there'll be a mark here that says 9 foot 6, 11 foot 9, and 9 foot 7. Well, you better be in the center lane. So
11.6, yeah.
I actually did that recently. I have a magnetic mounted antenna on my truck, on my car. So I don't drive the truck all that often. And I actually went through a drive-through very recently. It scared me to pieces. I thought I'd run over something.
Boy, yeah, boy, yo, 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 or where it just does this and it tips over and goes bam on the roof.
That would have probably scared me more.
I've done that recently. Like, oh, whoops. I pulled into a parking garage. I pulled into a parking garage and I heard a thump. I'm like, uh-oh. Darn it.
You pull into some place. I had a CB antenna on my truck one time, and it had like a concrete overhead, and all you're hearing is the whole time you're going down through.
Yep. Gas station overhangs.
Yes.
I would do that too. Yeah.
I have a quick question, Scott.
Yeah.
Do you have our emails in a great big group email? I'm curious if you're going to be doing any other classes in case you want to do a review.
I typically keep everyone's email. Whenever I do another class, I send it out to everyone.
Thank you.
So, but you've been getting like the day one recap, day two recap, stuff like that. Okay, good. Yeah, that means it works.
Nice.
So
it's nice to be with real people, though.
Yeah, isn't it?
It is.
So, and hopefully everybody's got a local club nearby that they can hang out with. Clubs are kind of like the lifeblood. Once you get turned loose, then they're basically your support group. And like I consider all the people who I've worked with in the radio clubs I've been a member of, I consider them all my friends.
Okay.
And it's been many, 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 many years. And the other thing that's really cool is anywhere I go in the world, all I have to do is look up the local hams, and I've got friends there. Because you share a common interest already.
Yeah.
Like I went to South America. Actually, let me go ahead and